machst, bevor du startest. Das ist mir zum Beispiel jetzt.
Passt, perfekt. Ich muss noch die Haus.
Okay. So, okay, everyone. We're waiting a couple more minutes for the people online, and then we're going to start.
even a bottle
So
of
we
wine.
will start at
A
15.
bottle of wine. Der Magnus hat gesagt,
5 more minutes. Okay, let's start.
Ja, Hello, welcome everybody to our international bootcamp. It's the second iteration this year. Sorry for the delay. We had some payment problems at the restaurant and it took some time, but we planned half an hour for the opening and we just shortened it, so we'll keep in time or stay in time. And I ask all the people who are on this slide, please, to come up to the stage. These are the organizers, people who were involved in the organization of this bootcamp, and we are happy that it's so full. We were not expecting this size, actually, and we are happy that we booked such a nice hall finally, so we fit in nicely. Okay. Yeah, first of all, we are really happy that you are here. But now let's start. Who are we? I would say we start with you, Andreas, and then Olga, Marius, me.
Yeah, very warm welcome also from my side. My name is Andreas Willisch. I represent AI Austria and Leoben Research, which you saw the logo of on the previous slide. We also, like my research department, sponsors the coffee break. So if the coffee sucks, you can blame it on me. Okay, well, thanks for the mic. So this is the second time around that we're doing this. It's amazing how many of you here are, and I can already tell you excel at decision making because you decided to come here, and that was a very, very good choice. So we, I think, really put together a very, very nice event, but there's only so much we can do. So we created the environment for you to thrive in, and now you have to walk the last mile to make this work. So you already, because of your decision making, are like, you know, awesome. But in order to make this legendary, you have to do your part. And that means to be open, to open your mind, to be respectful with one another, to engage in discussions, to form new bonds, find new collaborators, and really take something away that lasts from here. So this is what I encourage you to do. We're very, very happy that you're here.
That's you.
Okay, I'm Olga. I'm a data science student, currently at Salzburg University, and currently I'm writing my master thesis in reinforcement learning field. I'm also work at IDA Lab in SARL team with Simon, where we explore reinforcement learning, the power of reinforcement learning with industry. Yeah, and I would say my main message, if you have any questions, just come to us at any time at lunch and dinner during the session. We are happy to help you.
Thanks a lot. So my name is Simon Hierländer. Sorry. Sure, I have my own mic. I'm the main responsible for talking. I'm really happy that this happened. As I said, I'm leading a team at the IDA Lab at the university here. And we are trying to stabilize reinforcement learning, which is just taking off in my opinion. With this, I hand over to you, Catherine.
Thanks, Simon. Yeah, welcome from my side too. My name is Catherine. I'm here representing Fraunhofer on one side, also from AI Austria. With Andreas, we started the RL community. And yeah, from my side also, I think it's really cool to see so many people here. I'm excited to see what happens in the next 3 days. I'm excited to see what happens after these 2 days, which if you keep working on reinforcement learning, the community that we have here in Austria, it's small, but we're really interested, and yeah, welcome from my side.
Yeah, so I've attended last year's bootcamp. I've attended many conferences organized by Simon and his cohort. I'm happy to help you in this tutorial today. But yes, I think I'm involved myself because I know reinforcement learning is daunting, especially nowadays that they keep complicating themselves, and the problems where we apply them are also complicating themselves. And it's good that there are so many people who want to learn this. But it's just so that everyone knows it's okay if you're lost in the beginning. And if I bring nothing to this conference, it would be to be to rest easy, that it's not easy for many people.
So hi, I'm Marius. I'm representing Extensity AI. Come also from my background in machine learning. Did my PhD at Sept Institute of Machine Learning in JKU. And yeah, I had reinforcement learning in my background as well during my PhD and several other topics. And yeah, happy to have you all here. And yeah, I'm for the technical equipment a bit responsible to stream this all online.
Yes. So don't hesitate to ask any of us with any concern. No. This is important. So we do this. Why are we doing this? This is more some sort of a philosophical slide maybe, but I would say we are enthusiasts or professionals who want to make the world a better place. So our belief is that reinforcement learning is one of the key drivers currently in technology to make the world a bit better. And I speak for myself now that I think that AI has the potential to leverage human life somehow, to make it easier and better. And maybe it will at one point resolve many of our issues we have currently on our planet, as you all know. We keep this event free as long as we can. This means that in the background there's a lot of effort. And this is not easy, but it has also advantages. It is free of any other influence than our influence to some extent. There are some regulations, but all in all, we are free and we can move freely, and I also ask you to move freely in this event. One of the main things I see upcoming is now that collaboration between humans becomes more and more important. We can automatize more and more processes, but what really counts in order to succeed is that you start to form teams, that you start to collaborate, that you communicate, and that you use the power of humans, which is not that easily built into machines, because machines will replace a lot of things in the future, in my opinion. And this is why we are so happy that we bring you together and to discuss and to make use of this. So this is maybe what sets us apart from other technologies in the future. This is an impression of last year. It was a super cool event. I speak for myself, but I think everybody agrees. You see, we had many participants. It was half of the size of this year, approximately, and it was near in Itzling. And people gave us very cool feedback. We have several people who are here the second time even. And we have also established some collaborations in this event. So this is really cool. I would say we quickly scan through the agenda that everybody's on the same page, how the next days will look like, more or less. We start in the morning at 9:30. Tomorrow we have a keynote in the beginning, and lunch is at AG Beisel, as you know, most of you already. It's around 5 minutes of walking. It's a very nice place, very good food, as we learned today, which is very good. And if you don't want to join this, or you did not register for this, there's also one restaurant here in the building. It's called Eden, and several other places, of course, where you can go. There's especially one place, I say it now, it's the rooftop. You should visit the rooftop. You see Salzburg from a very nice perspective. And this is one of the main reasons why we've chosen this building, because it's so well placed. We have exceptional nice keynotes this year. This is Sergey Levine, who is forming the field of robotics and deep reinforcement learning currently. Many of you know him maybe. He's really impressive what he's done so far, and many of the algorithms I use daily are influenced also by him. So this is incredible. But we have also a very famous keynote speaker here in the crowd. This is Auer, who will give his keynote tomorrow, who influenced the field 25 years ago already, very impactful. So we will learn more about this tomorrow. I'm really looking forward to this. So I'm happy that he arranged to come. And also to Samuel Tosato, who is a researcher in Innsbruck and is doing really interesting stuff in reinforcement learning. Today we have a group picture at 5:15 at 17:15. So please, our photographer will come, collect us and brings us to the place where we take the picture, and then we can freely move. And then at 6, Sergey will give his keynote, which is a bit weird that we have the keynote that late, but he could not come, and there's the time shift, so it's 9 in the morning where he lives, and he said this is the earliest thing he can do. And we thought maybe we try it out. It's nice to collect everybody, and then we can go in the evening together somehow. So it's something we try out. Well, the evening program is better explained by you, Olga, I would say. So I hand over maybe the microphone. Yeah. Because most of these things were organized by Olga. So we are really happy that she did so much work on having such a nice program.
Yeah, I would say today we will have dinner in Argebeisel, and then tomorrow we will go to Device. Yeah, so I will give you details tomorrow about it. And Friday we will have a city visit. We will go up to the castle. Yeah, so I think it will be fun. Not only the session, but also our network sessions. Okay. Yeah, this is Wi-Fi details you can find. The network is plus event, username and password. We also have a coffee breaks. It will be at 3:30 today. It's just on the left, so it's easy to go. Yeah, and other signs you can find. There are also about backpacks. You can live here. I would say, yeah.
Okay.
This.
Just that you know, I don't need it. The coffee break is in the lower floor. So if you go outside of the lecture hall, you have to go downstairs. Or you use this exit here on the left side to go directly there. Just that you know where you can find the coffee then later on. All right, yeah, and backpacks, as you said, we can leave them here. We try to have a person who takes care of this so that you don't have to carry your stuff around with you, okay? Housekeeping, you registered and implicitly or explicitly signed some rules that we want to take pictures to capture the event. So this is another reminder that this will take place, please. If you don't like, then just get out of the picture. And we have a feedback form. We show this now. You can scan the QR code. We will show it again when you can give feedback. But please give feedback, because this helps us to somehow level this event and know what works out and what doesn't work out to make it a better experience each time. Okay? So, learning goals of this event. These are ideas. A boot camp comes from military background, is usually an intense training on something. And our idea is to give you an intense training on reinforcement learning to the extent we can do this in this short amount of time, given that we have several levels of expertise here in the room. So it should be an entry level. It should be possible that you can really start from 0 and go slowly towards understanding what is reinforcement learning. Is reinforcement learning something which helps me in my problem or I can use at any point in time? Yeah. And if you a bit more advanced, then maybe there are some challenges which trigger you. So the tutorial will have several levels, several layers, even challenging for myself. And We have lectures, we have hands-on coding sessions. It's in the program. You will learn to run standard experiments on standard environments, for sure. This is, in the beginning, something which is really tricky. We have several people who went through this phase already, who can maybe agree on this. So this is something cool to have. And there is some sentence here which says, we'll bring you from 0 to PPO and beyond, which makes many people smile, I assume. Well, let's see how far we can go. 0 is something, PPO is something, which is really everywhere. And beyond is even something more, of course. But take the chance, interact, ask questions. We have many experienced people, not only here, but also in the room. And reinforcement learning is not only a technology where you have some theory, it's an art to some extent, like deep learning was a while ago. Yeah, you need to have a feeling for what is happening now in my experience, and so on. And this can be given you by experts. Okay, for the ones who are totally desperate, as I was myself for a long time, we founded a self-help group. We call it Reinforcement Learning Coffee. So if you have interest, it's every first of the month. It's relatively informal. It's sometimes crowded, sometimes just a few people, but you share your experiences. You can present your problem. You can discuss your new idea on a paper. You can even really show off whatever is on your mind. And sometimes we just share updates, what's going on in our lives, in our reinforcement learning lives. Then this is the acknowledgement slide. Maybe it's not exhaustive. We try, but we try to thank the other lab, which gives me a job, and Olga, but all the other institutes, and also the speakers, of course, but also the volunteers. So there's Fabio and Erika. Fabio helps us locally. If you have questions, apart from us, he's volunteering. And Erika, I think she left. Or yeah, she was at the entrance. You saw her for sure. This dark hair. She will also help you if you need something. Yeah, and thank you for coming. Let's take off together. Let's have fun, collaborate, learn and enjoy. And that's it with the opening. Thank you. Passt. So you will hear my voice longer now, so you will get used to it. We have now a lecture which is the 0 lecture, which is really the entry level, where you never heard maybe of reinforcement learning before. And then this is also meant to have not too much formalism. It's more our intuitive understanding of things. And then I will hand over to Catherine. She will then introduce more formalism slowly. She will have the basic terminology, and then it increases. We will have then tomorrow a second lecture of Catherine, which goes toward what is the core of all modern reinforcement learning approaches. And then I will take over to give another lecture, which is especially on PPO, to maybe give you an idea on how PPO really works. And then we have this tutorial, which also uses PPO a lot in the afternoon. And then on the third day, we will have a state-of-the-art lecture given by Marius, and he also shows what he's doing. And in between, we have the keynotes. So, why reinforcement learning? Why now? I try to make it clear, but I start with this question. So many of you maybe know this slide already, but I like to show it though. Please don't answer. Who knows these people? I would say 1/3 even. All right, so this is Andrew Barto and Richard Sutton. These are main figures in reinforcement learning, in the development of the field of reinforcement learning. They were awarded this year with the Turing Award, which is a very high achievement in computer science. It's like the Nobel Prize of Computing, and they were recognized for the conceptual and algorithmic foundations of RL within the last decades. They also wrote the standard textbook of reinforcement learning. It's called An Introduction to Reinforcement Learning. You can download it freely, and it's like the Bible of a reinforcement learner to some extent. This is the, it's a bit hidden, but the number of citations of this book, I think. And at one point, it starts to really increase dramatically, and we will see why. This is around 2015, 2016. So, why reinforcement learning? This is a statement. We live in a world of increasing complexity, uncertainty, and interactivity. And reinforcement learning delivers a framework to solve complex problems from experience beyond static data sets. It's a growing paradigm, not only in artificial intelligence or AI research. It's also in engineering, economics, healthcare, and education. You see it spreading all around the places. This is a historical slide. First things first, it started in the 50s, so it's quite old, with Richard Bellman, who introduced the formalism and also dynamic programming. And then by Sutton and Barto in the 80s, 90s, the foundations of what we now call reinforcement learning were developed. In 2010, deep reinforcement learning started, a bit later actually, and since 2020, we have several real-world reinforcement learning applications in robotics in industry, and the reinforcement learning from human feedback is something we will see in a second. Well, what is the real power of reinforcement learning? There are many opinions on this, but I would say when you know the goal, but not how exactly to achieve this goal. Like in a chess game, you know you want to win, but finding a good strategy against a strong player is hard. And this is what reinforcement learning could, in principle, do for you. It's especially powerful when handcrafting the rules is hard or even unavailable. We can learn from sparse rewards. So when there is just from time to time a reward signal, there will other methods fail. And there are two main points mentioned when it's extremely useful. This is when you don't have any examples of desired behavior because the goal is beyond human performance, or there is no existing data yet, or you have an enormous search space and it's an optimization problem you want to solve with delayed outcomes. So this is really impressive. I show some examples now. This year, the gold medal, or at least gold scores were achieved in a mathematical Olympiad, in an international mathematical Olympiad. This is interesting because these problems are really hard. They are handpicked by experts who really take care that this is not out somewhere. It's not easy to find on the internet or so. And OpenAI and Google at the same time managed to achieve 35 out of 42 points on this. So what they did, this committee handed the questions to them. They solved it, but they were not allowed to announce 1 week after the announcement of the gold medal winner of the humans. Okay, there's a story behind that OpenAI violated this. They immediately said we are better, but Google waited, so only Google is in media, I think. There was reinforcement learning involved. We don't have too much time, but you can look it up. It's super interesting, and it's based on language. This is what I find really interesting. So they solved mathematical problems only at the level of language using reinforcement learning. Okay? Last year, there was the silver level achieved also by Google or by DeepMind, and they had still some rules inside. This was totally gone this year. All right, this is another impressive example. This is solving Rubik's Cube with one hand, just from the camera image by OpenAI, but this is a while ago. This was in 2018 already, but it's really impressive because solving Rubik's Cube with one hand, even manipulating the cube, is not easy. Yeah, you need training. And so they trained the robot hand to do that and solved the problem then using reinforcement learning. This is 2 years ago where reinforcement learning was stronger than humans in this drone racing, in the World Championship of Drone Racing. Also very impressive because these people who fly these drones have years of training, and so it's not straightforward. So it's very interesting, and it's called like a real-world breakthrough. Okay, then there are some examples from physics. I'm trained as a physicist, so this is very interesting to me. And I'm also involved in some of these experiments, like this is the awake experiments where you can control this machine or increase the performance by using reinforcement learning. And the other one is the tokamak, where this was done by, I think also DeepMind, where they learned to control the tokamak better using reinforcement learning. But there's a wide range of applications. There are some people maybe also in the room I mentioned here. This is from robotics to telecommunication, to assembly line optimization, to medicine even, or to accelerator control, energy optimization, robotics or cyber physical systems, logistic problems, and also here there are 3 things I just mentioned that are several places where you could start a thesis. If you are interested, reach out to us. This is some of them are in Salzburg, some are even in collaboration with other partners in Germany, like Deutsche Luft- und Raumfahrt. So some people are here. Just let us know. I just wanted to show you the richness of applications which are arising. Let's come back to what fascinates us as humans, maybe. As you all know, ChatGPT was released 3 years ago now, not even, but, or no, it was more than 3 years, but it changed the world, I would say. It changed the world of AI. It's one of the most successful applications ever released. So I just read that WhatsApp needed 2 years to reach 1 million users, and ChatGPT needed 2 months to reach the same number. So this is it's impressive. But how do they work from a very high level perspective? We have human buttons we put online at one point. Yeah, it might be written text, it might be images where we labeled, tagged these images, and then generative AI uses this data, trains from them, has some probability distribution in the background and mimics these patterns. And this is impressive to us. Yeah? So we can just, these are 3 examples where we just prompt something and it creates images which are maybe beyond our skills already. But we could have done it in principle. While reinforcement learning is impressive because it can go beyond what we imagine. There was this famous game where Lee Sedol played against AlphaGo in 2016 or 2015. And at that time, people believed that a computer cannot win this game of Go because it's too complex. And it's our strength, our intelligence strength. It was disproven at this time. And there was especially one move, because there were several experts. This game of Go was studied for thousands of years, and we fill libraries with knowledge how to play Go. And the computer showed us that there are some moves we highly underestimated. This was one move, it's called move 37. You can look it up, but it was beyond. So a human expert would never have done this, but it was labeled as brilliant by Lee Sedol, who himself was brilliant. Okay. This is just one slide to emphasize that also in ChatGPT there is a part of reinforcement learning. This is trying to make the model more behave like it should behave, for us at least. And this last training part was done by reinforcement learning, and they used BPO. So what we learn in the bootcamp is how does this BPO work? All right, so this was the examples. Let's move from prediction to action, more high-level formalism. What is reinforcement learning? Reinforcement learning tries to answer a fundamental question in artificial intelligence and machine learning. This is learning from experience / data how to make good decisions under uncertainty. This is a very powerful statement. If you think about it, it's maybe the foundation of intelligence. If somebody can behave very well given only little information, then we say, okay, this is an intelligent person. You spent usually 4 months in the machine learning course or in the reinforcement learning course to understand this sentence. So it has a lot of interesting components. But let's switch the perspective. This is the AI, the artificial intelligence-centric perspective, but there's also a mathematical perspective on reinforcement learning. The field is called sequential decision making, and there in the overlap, there's reinforcement learning. I mention this because when you start to do reinforcement learning as a computer scientist or whatever your background is, then you also always stay in this bubble usually of artificial intelligence. But there's a rich world which might be hidden for a while from you, which belongs to sequential decision making, which is really powerful. And in sequential decision making, you have several mathematical, well-established and well-studied fields like control theory or operations research or game theory or Bandits. But we stay for now with the artificial intelligence perspective. Artificial intelligence is the rich umbrella, and machine learning is what most of us perceive as artificial intelligence nowadays. And therein is deep learning, and then there's something called deep reinforcement learning. Reinforcement learning is not necessarily deep reinforcement learning, so there's still some part which is only or not using deep neural networks, but most of the things are deep reinforcement learning. So let's get a perspective, very basic perspective on how algorithms learn. In machine learning, we have these 3 classes. This is unsupervised learning, supervised learning, and reinforcement learning. And this is just to illustrate, which is most clear to you, most of you should be familiar with this, that so far what we did when we spoke about classical programming was that we had some rules, we put in the data, and it gave us the answer. Like, if a specific value is higher than this, then do this, and so on. Reinforcement learning is different because we provide the data and maybe the answers, and it implicitly comes up with the rules. This is called machine learning. So we say algorithms learn from experience. And in supervised learning, this is just what is involved here in this paradigm. This is learning from experience, learning from data. But then we have also a part of optimization. We have generalization, and usually we don't have labels. So let's say we have trees, images of trees, whatever, and we have our unsupervised algorithm. We put in the data without any label, and then it might cluster this into meaningful groups for us. So there are some parameters we can set, but generally it does the job. And then when it sees new data, of course, what it should do, it should put it in the right class. Supervised learning is different because we have a label. So this is the input data, which is some vegetables. And then here is the labels we give, that we identify objects and say, this is an apple, this is a pear, this is a banana. And then the models should learn the relation between our examples and the input. And when we put in new data, then it tells us it's an apple. All right, so far, all clear, I hope. Reinforcement learning is a bit different. Reinforcement learning is more interactive. It lives from the loop that you put in information, it takes a decision, it learns something, it collects new information, it takes a decision, and so on. This is a video of a chicken, and the chicken is our algorithm, and the chicken should always pick on this pink bed. This is the goal. So we just have the goal, and each time the chicken does what we want, we hand it over a reward. This is more or less the idea, also the source of the origin of reinforcement learning, the motivation. So we have the world, the chicken is in the world, sees something, and then does something. It picks somewhere randomly maybe, or luckily on the pink bed. And if it does so, then it gets a reward. Otherwise, it gets no reward or zero reward. And within this loop, it starts to learn the correct behavior. That's the idea of reinforcement learning. So learning through interaction with the environment, and the goal is to maximize the sum or the amount of food it gets, right? In the end, our product, what we have is a function which maps each observation to a specific action. So the chicken sees something and does something, and this is the function we are looking for. This is called policy. So what involves reinforcement learning, what sets us apart from other paradigms is that we learn from experience, we still have optimization, but we also can handle delayed consequences. We have a problem of exploration, we will discuss now, and generalization is also involved. So the optimization part is to find an optimal or near optimal way to make decisions to achieve our goal. There's the explicit notion of a decision utility, a reward function, and one example would be what is the fastest way from one point to the other in a city. This is the optimization aspect. Delayed consequences is something which is very interesting, because we are not good in estimating delayed consequences, maybe. It's, for example, saving for the retirement. Now, I cannot buy this or that, or I cannot go out, or whatever. But at one point, it will pay off. This is hard for us to grasp, but yeah, algorithmically it's possible, but also tricky. Yeah? Just that you have an idea. There are two challenges mentioned here, and here are two words coming up. This is learning and planning. When I say planning, planning means we have a model, we know how the world works, and we try to figure out within this model what is good. We know exactly how the chess game works, and we try to find what is the best tactic therein. We could plan without ever playing a real chess game. We have a perfect simulation. Learning is different. Learning is directly via trial and error. You don't know the rules, and you learn the rules along the way of the game, and then you learn how to achieve high rewards. This is the difference between these two things. In planning, it's hard. In reinforcement learning or in learning, it's a bit harder, and this is called the credit assignment problem. What led to a high or low rewards later on at an early time step? Exploration. Exploration is that our agent is like a scientist and has to learn via trial and error. And think about learning to ride a bike. You will fail many times until you start to do something meaningful. And at one point, we have to say, okay, I don't want to explore anymore with an algorithm. We want to take what we already learned and stay with this. So this is the exploitation. So exploration is sacrificing something in order to maybe learn something better later on. Exploitation means, okay, I take it immediately because I know that it's good. Yeah. So the important thing is that the algorithm only can learn about decisions it made. If it didn't see this, you can only guess. So only for the decisions we made, we can estimate or start to estimate the reward. That's totally logical, but you should think of it. You don't know if you decided at one point to do something, what would have been the outcome for the other thing. And our problem in life is that we only can take one decision at one single time step, so we never know. It's like our life is censored. We don't know what would have happened if you would have gone to Vienna tonight and not to Salzburg. Yeah? Okay. Generalization. Generalization is the aspect that if you experience new situations algorithmically, how good are you behaving in this new situation? Yeah? So here, okay, the policy is a mapping of accumulated experience to action. But why can't we just reprogram a policy? Even in this example here, this is, who knows it? A game, a computer game? Okay, I say it. Some of you at least raised their hands. It's the Atari. And Atari, this was an impressive moment in reinforcement learning. It was around 2014, 2015, when deep reinforcement learning was the first time producing really impressive results. And this is was done by David Silva. They learned to play Atari games. They have had 57 Atari games, and they learned to play on a majority of it better than human experts, using reinforcement learning, only using the image of the video game and the controller, as a human would do. Yeah? And they used one algorithm to perform on all these games that well, that changed the world of reinforcement learning. And now, this is just an example why we cannot program it. You can estimate now how many possibilities you can have for such images. These are 100 by 200 pixels. We have 256 gray levels and 3 color channels. So this is a huge amount. It's more possibilities than atoms in the universe. It's not possible. It will never happen. This is called generalization. just to flash something again. This is the loop of information and learning, making decisions. What we usually do is we have, I go back, we observe the world, we collect data, and then we start to model. This is done in science and everywhere, of course. And then out of this modeling, usually you derive a decision. So you have a model, the model tells you what to do, you take actions, and this changes the world, and it might invalidate your modeling. And this loop should be closed by reinforcement learning. So you start to take the consequences of using the model into account in order to solve the problem with keeping the consequences in mind. So we have here the comparison. Supervised is like a snapshot of a chess game, while reinforcement learning is the chess game itself. Okay, this was more or less without terminology, too much terminology. Now we introduce some terms of reinforcement learning. So this is the loop, the reinforcement learning I showed with the chicken. There sits the reinforcement learning algorithm. This algorithm interacts with the world. The world is modeled mathematically to make it accessible to the algorithm, and the algorithm gets some state and reward when it took an action. This world modeling is called Markov decision process. We will learn more about the details in Catherine's talk concerning the mathematical aspect. I will do it more informally, but there's also something which is called a MDP. This is a partially observable Markov decision process, and this is what we usually deal with. We barely deal in real life with a perfect chess game. We have a lot of uncertainties, and we have to somehow model this appropriately, and we will see some examples, but this makes life a bit harder for us. And then there is this last part, which is us. So even if this is done very well, you need a lot of fine-tunings until your experiment will be successful. So this is the outer loop. What is the world of an agent? So this is the loop as explained, just shown differently. We have the agent as the brain and the world as the world, and then we loop. And the goal is to find actions which maximize the total expected future reward. This is our goal. Expected is here colored in green, so this is an expectation. The world can be stochastic. We will see what this means. And we want to balance. Okay, why is it highlighted? Because this is not the only way you can do reinforcement learning or estimate the outcome of an event. You can even start to model the distribution, and you do distributional reinforcement learning. We keep it with the expected reward still. So in all of our slides, we are speaking about the expected reward, I think. You have to balance immediate and long-term rewards, and you have to find a strategy to achieve these high rewards. This is an example, web advertising. So what you do is you have a web advertisement you show to people, and they either click on it or not. And you have to select the best advertisement, for example. This is a sort of a bandit problem. There's no direct delayed consequence, or we try to model it as simple as possible, not to take too much information into account concerning the user. We could, but the simplest way is that we don't know who is in front of the screen, and we want just to see what is the best advertisement. Another example, household robot. Let's say we want to build a robot which cleans the dishes for us. And what it can do is or it at least puts our dishes into the dishwasher, make it simpler. What it can do, it can move the arm, it sees the dishes, and it should learn to put the dishes from the table into the dishwasher. And you can say, okay, a reward of 1 if the table is empty. The question is, does this make sense? I mean, many things can happen. So then the reward is not designed very well. It either puts it into the dishwasher, but it also could hit all the dishes on the floor, and then the dish is empty. So a strategy might be needed to achieve high rewards. This is another example. This is blood pressure regulation. Let's say we have to decide either to do sports or to give a medicamentation. And if the blood pressure is in a healthy range, then we give a reward of +1. If we give a medicamentation, we give a slightly negative reward because there might be side effects. Then we have to start to balance already between the immediate and long-term rewards. There's another example. This is the tutor application where we want to teach pupils to learn how to do addition or subtraction. And addition is easier than subtraction. So we would give, for example, a +1 if the example is solved correctly, and a -1 if the example is not solved correctly. So can you imagine what this would imply if we do that in this setting? What will happen immediately? What will the pupil learn to do? Yes. So very, very likely it only starts to learn addition because it gets immediate reward, and subtraction will be left out. All right. We formalize the interaction with the world in discrete time steps. So in each time step, and this is now this T here, we do something. We start at the time step 0, for example. Then we have this OT, which stands for observation, and the reward T at this time step 0. So O0 and R0, and then we take action 0, A0. And then the world emits a new state and a reward, which is R1 and O1. What this does is that it creates a sequence, of course. If we follow for a while, it creates O0, A1, O1, R1, so the first reward is left out for some reason. It could be in it, it is not necessary, but we have this sequence, and this is the history of what happened. And the agent selects an action based on this history. So the information in the history should be sufficient to base the decision on. It should be sufficient to derive what we call a state. So this is the O for observation, but we have here a state S. And the state S is, it has some properties we've seen a second, but it's derived, and we don't see this. Maybe we can remove this a bit. I'm not sure. No. Maybe Marius can do this. This is a function of the history. So S of t is just a function of H of t. Yeah. The world state, as I said before when we were talking about Markov decision processes, is this S of t, and this is usually not directly accessible to the agent. Only in a few cases we have this S of t, Otherwise, we have to think, what should we do? How should we measure the world? What do we have to take out of our history in order to get a meaningful state? And sometimes we have the state, but it's not even necessary to have the full state. So it may be known, but it's not needed by the agent. So we simplify. And this is the internal representation for the agent. This is what the agent sees from the world. Then there's a mapping in between, and then we have this state, and this is how the agent bases its decision. In general, it's a function of the history, as written here. Now we see it. But it can include everything you can imagine. Some parameters about the optimization technique inside, for example. Meta information, like the status of the algorithm, number of calculations performed, etc. Or information about your problem. How many steps do I have left till something ends, for example? And one very important point is the so-called Markov assumption when it comes to this state. The state information should be sufficient statistics of the history. A state S of D is Markov, so there are only a few formulas here. This is one of them. The state S is Markov if and only if it's, this is a conditional probability. So if the probability of reaching SD plus 1, given S of D and A of D, is what you need. And you don't need the history. So the history or the representation of parts of the history is sufficient. This takes some time usually to be digested, and I sometimes also have situations where we have to discuss, is this now Markov or not? But for me, what helps me a lot is to think about the chess game. No matter who played before, when I come to a chess game and I'm in a specific situation, I can end the game. So the chess game is Markovian, and this is how you could look at it. If you arrive at a situation and you have your state information, it should be sufficient to solve the problem from there on, neglecting all the past. So the future is independent of the past given the present. Okay? Is the high blood pressure control example we had before, when we just measure the blood pressure and we say if it's above a threshold, it's not good, if it's below, it's good, is this a Markovian system or not? No, for sure not. Because there are so many influences which impact the blood pressure itself. So it's not a good way. In any case, all these medical problems are really tricky because of that. The website shopping one can discuss. Is it Markovian or not? When you only look at what the customer looks currently at and then try to see what he will buy then, usually it's not Markovian, but most of the times it's modeled as a Markovian system. The interesting aspect of Markov systems and why they are so popular is that you always can make a system a Markov system by just including all the history. It's just to find a trade-off between how much statistics you really need from the history and how hard the problem gets. Because with each additional entry in your state space, the complexity increases exponentially in the worst case. So what we do in practice is we assume, okay, our system is Markovian, and let's try out, more or less. Or we take some states of the past But as I said, it has a strong influence on the computational complexity, the required data, and the resulting performance. This changes a bit nowadays. We have now very fast tools like recurrent neural networks or LSTMs who can digest the history very fast. So the computational complexity is not such a tricky aspect, but you should always keep that in mind. So when we say a system is fully observable, then the state is the observation. If it's partially observable most of the time, then the state is a function of the history, and we cannot see directly the state. We have to infer it, like a noisy measurement for a robot. Maybe it has to wait for some more pictures until the noise cancels out and it can do something. Okay. An example of a partially observable system would be the poker game. So the poker player only knows what he has on its hand and can just make a belief state on what the others have and what comes next. Healthcare, as we said already, we don't have access to all parameters of our body, or more and more, but nevertheless, it will be always a partially observable system. All right. The simplest form, as we said, of such a system is a so-called bandit. In the bandit, there's only one state. And we have to take the right action. Let's say we have several things we can select. We have to find out what gives us the highest reward. So the actions have no impact on the next state because there is no next state. There is no delayed consequence. There is no reward. Nevertheless, they are super important, as we learn tomorrow, I assume, to study the trade-off between exploration and exploitation. And don't underestimate bandits. We can learn a lot from them, and this is a research field. Okay. This slide is about stochasticity. So far, we didn't speak much about how such a state can look like, or how such an observation can look like, or how such a reward can look like, or how our action impacts the world could look like. And it could be totally stochastic, which means that instead of going left, I decide to go left, but I go right. Yeah? There's a likely probability that this happens in several systems, and sometimes we introduce this even on purpose. Think about a vacuum cleaning robot who is not making it on the carpet, because I see this very often at home. At one point, it decides to do something else. So there's some randomness in how to take actions. This is an exploration topic, but just to give you an idea of what is meant by randomness. So or by stochasticity. This is a philosophical statement maybe, but I think most of the cases, if you have sufficient information, then we can design a deterministic model of this. Now we notice that Newton mechanics is deterministic. There was the belief that we can predict the future till infinity, or we can go back to how far we want to go. It's just a question of how much information we have at hand. If we would have the position and the velocity of every atom in the universe, we could predict in principle everything. So it's not that easy to do the calculations. It's intractable. We cannot measure it. It's just infeasible. And so we have to come up with a trade-off in most of the cases to take some uncertainty into account. So we create a model which is slightly wrong with some uncertainty, but we get the advantage that we can compute it. This is most of the times the case. Think of a coin flip. Maybe this is easier. A coin flip, we say, okay, it's 50-50 that it's head or tails. From statistics, we have this experiment. But you could, in principle, model, and they did it, because in soccer, this is very crucial. You flip the coin, and then one team gets the ball, and they did intensive studies, and they said, okay, this coin flip is not fair because of the physics behind. So it's a deterministic process, and they could find out that flipping the coin has an impact on how it lands. But okay, I just want to give you the idea about what is stochasticity and where it comes into the game, but we can treat with our Markov decision processes stochastic outcomes. This is an example. This is the Mars rover example. This is a simple example of a Markov decision process model where we have the robot here in state 4, and we have 7 discrete states we can occupy. So the Mars rover is in one of these 7 states here in S4, and it can move left or right. And for example, in state 1, we have a nice discovery. We find a nice mineral. But in state 7, we find water. And this is a super discovery. So in state 1, we give it a +1 reward. And in state 7, we give it a reward of 10. This is just to illustrate you how such a model looks like. The algorithmic components, quickly. And this is now slowly introducing the terminology of reinforcement learning. We can have a model of this situation we saw before of the Mars rover. This is a representation of how the model behaves when we take an action in this world. But it's a model. Then there's the term policy. The term policy is what we are looking for. This is the mapping from each state to an action in order to achieve the highest cumulative expected discounted reward. And there is something which is called the value function, which is very important, which should measure the quality of a certain state in accordance to following a policy in achieving the highest reward. So the future rewards from a state or state action when following a certain policy. This is the model. So this is the internal representation of the world, of the agent. It can interact with the model without interacting with the reality. There are 2 kinds of models. This is the transition dynamics model, which predicts when I'm in a state, I take an action, what is the next state? The reward model predicts what is the expected reward from there. As I said, we just look at expectation values when it comes to the reward, and this is the model of it. So here, as we saw before, this head just indicates that this is a model parameter. So our head is 0 everywhere. This is the internal representation of the agent. But as we know, this is not correct. So it can be wrong, but it can still be useful because the reward here was 1 and the reward here was 10. Okay, this could be a totally random policy where I'm in a state and no matter what action I take, I end up with 50% probability in one of the consecutive the neighboring states. Yeah. Okay. The policy is, and this will be repeated, I think, by you, Catherine, that is the mapping from each state to a specific action. It can be deterministic, but it also can be stochastic, that there is a randomness, and with a certain probability, I take a certain action. In a vacuum cleaning robot, yes?
The transition model and the reward model is traditionally then a model-based model.
Yes, exactly. If you use this, you train a specific model of this, then, and you use it then to solve your reinforcement learning problem, but we will come to this. So is this a deterministic or a stochastic policy? So we choose always to go to the right, no matter what state we are in. The simple answer. Yes. Okay, this is the value function. As I said, is now the long formulation, expected discounted sum of future rewards. This is a very important term in reinforcement learning, and we have classes of algorithms which are value-based, which use this notion. But in all reinforcement learning, we need this function somewhere in order to estimate how good our policy is. So it just sums up our current reward. We're in a state S here, and from there on we want to find out what happens if we follow a specific policy. And this policy tells us what to do in which state. It's the mapping from a state to an action. And this is just the expectation following this policy, what happens in the future with this gamma here. So it's R of t plus gamma R of t plus 1. So I take an action between, I take another action in between, I end up in another state and in another state. And then I have this gamma squared and this gamma cubed. So there is this gamma term which we call discount factor. And the idea is that we have control on how far we look into the future. So if this gamma is 0, then only the first term is left. If this gamma is 1, we take all the terms into account. But we can control this. So this is between 0 and 1. Yeah, it's between myopic and farsight. This value function is the quality of our policy. It tells us how the quality of our policy in a specific state. How good is a specific state with respect to a policy? And then I can start to think, this policy has a higher value than this policy, so I would prefer this policy instead of this. Yeah, it's can be used to quantify how good or bad condition or action is. Okay, this is next step, sorry. Well, it's to compare policies. This is an example here. This is the previous example. We have a discount factor of 0. This is the tricky part of this slide. So the only term which is left is the first reward, no matter what happens afterwards. And this, in this case, is 1 on the left and 10 on the right and 0 everywhere else. Now we come to this question of Hannes before. Model-free versus model-based. Model-free algorithms are called model-free algorithms because there's the contrast to model-based algorithms. This can be discussed, but in reinforcement learning what we mean is that we have an explicit notion, an explicit formulation of the value function and or the policy. In contrast, model-based has an explicit notion of the model itself. And this is illustrated here. We have here the world, as we saw it before, the agent which takes an action and gets some feedback. And on top of this learning loop, we can also learn a model on what would happen. So I create a map of the world, and I can start to plan within this model without ever interacting with the real world, which has advantages and disadvantages. It can accelerate the learning process a lot, and it can help you in many situations. But this is the difference between these two worlds. I hope this is clear. So in model-based, we can have a policy and value function as well. But what is for sure, we have an explicit model. Okay. This I skip because we see this in any case. These slides will be online anyways. There is a number of really good textbooks in reinforcement learning. This is a subset with some additional information. You can look it up, or you can reach out to me or to anybody. At least the first one is the Bible, the Sutton and Pato. You should have opened at least once in your life. Okay. Then there are some really important libraries. You can look it up. We will focus on stable baselines and RLib in the tutorial. Very common, very stable, very good libraries. But these are not the only ones. Every library has its advantages and disadvantages. But usually it's about the community which is behind the library. Because if there's a huge community, it might be very good, and the maintainment will go on, and it's debugged. This is not, sometimes they discover bugs years later in a reinforcement library or in any library. Just that you know that this is what you should look out for. And stable baselines is one of these libraries where they really try to make it bulletproof. Okay, so that's the end of this 0-level lecture. You made it through. Just a quick summary. And then I think we have a break of half an hour or so. Yes. Okay. Reinforcement learning is learning to act, not only to predict, in contrast to other paradigms in machine learning. We saw that there are MDPs, and we will see that they can be made very powerful using deep learning. Reinforcement learning enables strategies beyond human intuition. This is something I always emphasize. And we see that it's spreading all over the world, so it's always good to have a good idea on what reinforcement learning can do for you and what it is. We didn't discuss too many of the challenges. We will, in the second part of my lecture, at least touch it a bit, but reinforcement learning is powerful but also tricky. But it's for sure unique in the AI world, and it takes your data into decisions. And hopefully we can bring you from this 0 level now more and more towards having concrete ideas in how to apply reinforcement learning in your problems. All right, that was my last slide. Thanks a lot for listening. Yeah. So I repeat, coffee break is downstairs. You can either exit here and go down, or you take this shortcut here.
Okay, welcome back, everybody. Let's just wait for the last few people to come back in. Careful walking over the cable with coffee. It's also being streamed as you walk past, so. Okay, so the next session, as Simon mentioned a little bit earlier, this is really about taking all the ideas, the concepts that he introduced in the first session and making them more concrete, building now talking about the mathematical foundation and how we can really build on this to then solve the reinforcement learning problems. So I hope that a lot of the ideas or a lot of the concepts we're going to talk about right now, you've seen now in the last lecture. Maybe a lot of you have seen them generally if you've worked with reinforcement learning before. But the idea is to really build up from zero, build up the framework that we're going to use, that you can kind of use to balance yourself on or to stand on for all of the rest of these algorithms. And one thing I think is important and kind of the focus of this bootcamp is a lot of these algorithms you can just find online now. There's really good algorithms. You can just use them, let them run, they work. And so one focus that we want to do is really going back, how are these algorithms built? What are the differences between them? So you can understand a little bit more what you're doing when you download one of these algorithms and just let it run in your own environment. So my lectures will be in two parts. One is today, the next part will be tomorrow. We're going to start again with a little bit of motivation, try and formulate our problem specifically. That will bring us to markup decision processes. You've already seen what that is, but how can we define that? That leads into value functions. We've also already seen it, thanks to Simon. And then Bellman's equations. And from Bellman's equations, we'll see, okay, now we can start talking about what kind of methods we can use, what kind of algorithms we can use to actually solve them. That brings us to our four main categories that I'm going to talk about: dynamic programming, Monte Carlo, temporal difference, and then policy gradients. And from there, you'll be able to go to PPO and beyond after that. So this is really the building blocks. This is like the Lego. This is really the basics. But if you have a good base of the Legos, then you can build something cool on top of it. So let's start with the motivation problem formulation. And this is a little bit more now concrete than how Simon introduced it. But it's the same idea. We have sequential decision-making problems in dynamic environments. And that's the problems we're interested in solving. That's what brings us to this bootcamp. That's what brings us to these techniques in general. And what we're trying to do, we're trying to ask an agent to make a series of decisions over time for us, with each decision affecting future outcomes. So this is a little bit different. If I make one decision now, and then it's over, I get my reward. That's a different setup as I make a decision now, then I have to make another decision, and then I have to make another decision, and all of these impact each other, and it kind of compounds throughout time. Our environment that we're looking at is dynamic, so it means it can change in response to our agent's actions. So when I make an action, it changes the environment. I make a new action, it changes again, and this is a dynamic process. And what's our goal? It's to learn a policy. So as Simon said, a policy is what actions do I want to take? I want to learn what actions should I take to maximize some sort of cumulative reward that I define or minimize some costs over the entire decision-making process. So one of the most famous examples is probably in chess. Like we saw, I know I want to win the game. I just don't know how to do it. What moves do I have to make to win? That's what I'd like to learn. That's what I'd like to be able to automate or optimize for whatever goal that I'm working at. And reinforcement learning really describes this computational approach to learning from interaction. And that's what we're going to focus on today. And what that breaks down to is learning how to map situations, so that's our state space, into actions. So that's kind of describing what my policy is doing. I have some state space. I want to take some actions in order to maximize my numerical reward signal. So I've somehow been able to define a numerical, a quantifiable reward at the end of the day. And the way that I'm going to do that is through a trial and error search, basically. And I have a delayed reward. I don't get my reward immediately after. And if I were to get my reward immediately, there's other great control techniques which are maybe a little bit more efficient to finding the best control policy. Okay, so let's warm up. Simon already introduced the bandit problems. So we're going to warm up and learn a couple of important concepts with the bandit problem. As he said, the bandit problem is a little bit of a simplified version. It's non-associative. We have only one state. So we basically don't have different states we can move into. We're just in some certain state. We have a few actions we're allowed to take, and each action can give us a set of rewards. So it could be, I don't know, you have a set of doors and you can open the door and see what's behind and you get a reward each time. But then you close the door and you're back in the same state and you always have the same actions available to you. So in this case, I'm faced repeatedly, in this case, with k different actions. And each action has an expected or mean reward when that action is selected. So I don't always have to get the same reward. It could be a distribution of rewards that I get by taking that action. And this mean or expected reward that I get over this distribution is called the action value. It tells me how valuable is this action to me, how good is this action to me based on this reward that we've defined. How do we really mathematically write that? Well, that's just what's written here. So Q is our value function. It gives us the value, or basically how good is the action, in this case A. And what does that mean? For the action A that I take, it's the expectation value, because this could be a stochastic distribution of rewards. It's the expectation value over all of the rewards I could get from taking this action. And if I were to know this, if I were to know this value for every action, then I've basically solved my problem, because I know how good it is to take every action. I can just look at all of these. I see I have k actions. I look at all of my k values, and I say I will take the best one, because I want to maximize my reward. So if I were to have this function, basically I would have my problem solved, and I would just choose the one that I want to choose. So we're assuming that we don't know this value function off the bat. So if I don't have it, well, instead of having the actual value function for each action, I've got an estimate for that value. And that estimate, we don't know how to get it yet, but that estimate I'm going to write with the capital Q to distinguish from the actual function, which is the little q. So this capital Q function, this estimates my little value function. And my goal is to have the best estimate possible, so to make the most informed decision on which action I should take. So now we need to take a couple of things into account. If I have an estimate of my action, say my estimate, I've seen that one action gives me a pretty good reward. So now I think, okay, perfect, I just keep taking that one. I keep getting a pretty good reward, and I'm pretty happy with my situation. That would be called exploitation. That's kind of taking the greedy action. It's saying, with the information I have, I always do what maximizes the reward at the moment for me. But the point is, especially if I'm working with an estimation, I mean, this policy would work if I knew the actual value function, because then I knew I would be doing the most optimal action. But if I don't know, if I still have an estimate of my value function, then maybe I don't know if I just haven't explored enough to realize that another action would be better. And that's what Simon described as this trade-off between exploration and exploitation. I want to make sure I'm exploring a little bit my entire action space before I'm settling down and saying, okay, no, this is the action I want to take. So in terms of exploration, you could say, in order to improve my estimate, I want to try things that maybe don't look optimal at the moment, but it allows me to gain more information about my system. And when I'm confident I have enough information about my system, then I can work greedily and just take the optimal action based on the information I have at the moment. And in general, I think one point is that it's not too important to have a specific exploitation strategy. It's just important to do something. So it's important to explore your space in some way. And in general, you just have to make sure you're exploring. The exact strategy doesn't need to be so sophisticated. And we see in many cases actually really one of the most basic strategies you can choose. So we haven't talked about how do we actually estimate our value function. So one way we could estimate the action value function is just by taking all of the rewards I've accumulated by taking a particular action and averaging them. So say I choose action A. I've done it 10 times. These 10 times I've gotten this set of rewards. I just take the average of all of those rewards, and I have a good estimation of what the average reward is for that action. Maybe if I were to take 10 more, I would get a better average. But as I improve my sampling, as I increase my sampling, this estimation is going to give me a better picture of the actual average reward. So that would be what's written here. You just take the average over all the rewards you got. And then if I wanted to do exploitation, I would just take the maximum action, so the argmax of my estimated value function. That would give me my greedy action. And in order to get a little bit of exploration, we do the epsilon greedy, which is one of the most standard, I think, exploration strategies. So you take with a small probability epsilon, I just select an action randomly. And if I do this, and I sample many times, then my estimated value functions will give me more information about my whole bandit problem. And I can, at the end, when I think I have enough samples, I can just act greedily all the time and choose the optimal action. But we need a way to keep track of our action value function in a more efficient manner. So if I were to do it in this case, I would have to keep always my sum of all of my possible rewards, which would get bigger and bigger and bigger as I take more samples. So again, this maybe seems straightforward, but it's an important building block in this whole discussion. We want an update rule which stays constant no matter how many times I've sampled, no matter how many times I've tried to take an action, or no matter how many time steps I've already done in my learning process. And that's what this is. So if I take the estimate that I have at time step n, and then I just add the difference to the sample that I've taken and divide by the number of samples I have, then I can update my estimate to qn+1. And this is a general form of an update rule where my new estimate is equal to the old estimate plus some step size, and then the difference between the old estimate and my new target. And this new target is defined based on the little bit of new information that I've gained in this one step. And so this is a fundamental update that we'll take on with all of these algorithms that we use in the later part of the lecture. So in this bandit problem, it's still very simple, but I think there's some very fundamental things to learn from it. The first one is, what is an action value? So how did I define that action value, and what does it mean? Balancing exploration and exploitation in order to search my whole space, gain information. It's this trade-off between I already know my system, so I know what I want to do, and I need to make sure I get enough information to know that I know my system. When I say greedy, that means I'm just taking, based on the information I have, the one that will optimize my reward. And if I'm saying epsilon greedy, it means I do that most of the time, but for some small epsilon, I take a random action. So the greedy and epsilon greedy are terms which will come up much more often in all of reinforcement learning, I would say. And then the last point is this incremental implementation. So I have an estimate of my desired value function, and every iteration, every time I gain a little bit more information, every step, I'm going to update it with a little bit of this, what was it before, and what would it need to change in order to, what is the difference between that estimate and the target that I've now learned about through my new step. So with those 4 components, I would say we're ready to go to the actual reinforcement learning problem, which is then introducing the state space back. If there's any questions, ask. You can just raise your hand during the lecture, so don't hesitate. So the second point is now moving really onto Markov decision processes. And what's the difference here to what these bandit problems are is in the bandit problem, we just assumed we could take all these actions and we would just repeatedly take actions from the same initial state the whole time, and we would always return to that same initial state. And what did we learn about Markov decision processes from the lecture 0? This includes now an environment where we have different states, and the states are going to be impacted by the actions we're taking. And so this is really, it's our model for sequential decision making when outcomes are uncertain. That's a sentence I think you also had. And it's kind of the mathematically idealized form of the reinforcement learning problem. And the point is, in order to make any sort of statements about how good an algorithm works, how good this technique works in general, you need to have some foundation where you can make quantitative statements, and that's the MDP. In real life, things don't always look as pretty as they look in this diagram that you see everywhere. States aren't always well defined, rewards aren't always well defined, even actions might not be as well defined, but we need to have some sort of mathematical basis where we can make statements on. But this is important to keep in mind, especially, so I'm not sure what applications you are all working on. I'm working a lot on industry use cases. When applying some of these results to then industry use cases where these things aren't always clear, there's a lot of, I would say, messes that come up with it. So just keep that in mind when then really applying this in the real world. The reason why things don't always work as well as they would with these perfect environments is because you're leaving this mathematically well-defined realm. Which is another argument to really learning the basics, because even just plugging in these finished algorithms, if you're not sure where they're applicable and where they work, you don't understand your own results as well. Okay, so yeah, just to summarize, this is really the MDP is our framework that we use, but it's a trade-off between what do we want mathematically so that we can make concrete quantitative statements, and what do we actually have in the real world, which is pretty messy sometimes in the end. So keep that in mind. Okay, so we need to make a couple of definitions now. We always talk about RL agents, and the RL agent is just responsible for taking the action, selecting the action to take at each state. The environment, so the bottom part of this little loop, responds to these actions and presents new situations to the agent, so it gives the new state to the agent, and it also gives the rewards back to the agent. And the environment is the thing that we're trying to then understand better. The agent and the environment interact at each of a sequence of direct time steps. And at each time step, the agent receives the environment state. It's given by some state in the whole state space. The agent selects an action, one action within the whole defined set of actions. And we get a numerical reward from its previous action. And as we saw previously, that gives rise to a trajectory where you have a state, you take an action, you get a reward, you end up in a new state, and this goes on and on and on. I think maybe we are even not consistent in our notation, I just realized. This is something also kind of annoying in reinforcement learning. Where you put the 0 and the 1, where does the reward get? Is the action with the previous state, or is it with the... Anyways, be careful when you're looking at it, because I even think we have different notation, actually. Yeah, sure.
So notation-wise, you used calligraphic R.
Yes.
For, let's say, the reward set, right?
Mm-hmm.
But is there actually a reason for using this notion? Because it always needs to be a real number, otherwise we cannot phrase the sum of the commutative
Yeah.
reward. Whereas in action and state spaces can be very abstract spaces.
Yeah. It's true. Yeah, true. Yeah, the question was, is there a reason behind using calligraphic R in the set of all possible rewards? Because actually the rewards are much more limited than what you can take for an action and a state space, and I would agree. And this should be a number. And the dynamics of our MDP, so we have this trajectory, and we also discussed the dynamics of the MDP is defined by the model. And the word model is also used in different contexts in very different ways. So in reinforcement learning, the model is the probability of, if I'm in a state S and I take an action A, what is the probability that I end up in a new state S prime with some reward? And this could be, if this was deterministic, you would just have a probability 1 for some new state. But that doesn't have to be the case. And it doesn't have to be the case that you always get the same reward. So that's why we're always working with these probability functions and expectation values. But I would say also for someone who's here maybe learning about reinforcement learning for the first time, it's easy to just think back to the deterministic case in all of these. Then everything goes down to no probabilities anymore. You just end up in a particular state. The expectation values are trivial. And that helps kind of to understand some of these equations that seem sometimes a little bit more complicated than they are just because of these probability distributions which are floating around. We also talked about the Markov property, so I'm just going to repeat it to be consistent. So what does the Markov property tell us? It tells us that the probabilities given by this model that we have are completely characterize the environment's dynamics. So it doesn't matter how I got to this state, as soon as I'm in this state, that's all I need to know. It's sometimes called memoryless. There's also a lot of work done on Markov chains, which is a similar idea, except you're not taking an actual action. It's just a series of values. And yeah, as Simon said, it's sometimes a hard definition as to what is Markov and what not, because if I were to include more information about the past, then sometimes you can kind of, trick yourself or think you're in a Markov, you have the Markov property because you're just including a lot of history about the past, but your state space is getting larger and larger at every time step because you have to keep including more information from the past. So I think defining which situations are Markov or not is not always as trivial as it maybe seems, which are also some of your examples. Like, is a medical process Markov or not? I think it's a little bit of a gray area in most cases. In most of these real world cases, especially where you don't know how much information do I have access to in order to define your state. And so as an example, I'm taking the Mars rover to kind of create a storyline thread. So like, this was our example MDP. We have the Mars rover. He starts in the middle state. And I have a model here which is probabilistic. We have two actions. I can move to the left or the right, and the rewards stay the same as what you were describing. If I end up in the left-hand state, I have a reward of 1, and if I end up in the right-hand state, I have a reward of 10. I think it was water and something else you were finding. And if I take an action R or L, if I take that action, the probability that I move in that direction that I wanted to is 1/2. The probability that I end up staying where I am is 1/3. And the probability that I actually move in the opposite direction is 1/6. So it could be I want to move to the right, but something with my wiring is bad, and I end up moving to the left. So this defines my model. And with this information, I actually have completely defined my Markov decision process. So I have a very well-defined problem here. And we're going to use this example now as we see what happens if I didn't know this, how would I find out what action to take, et cetera. In this case, it's actually easy to know what action to take, but those are good. It's a good lesson to learn. It's good to start with an example where you know what the outcome should be to know that you're doing everything right. So let's move to, well, now we have our Markov decision process. How can we define what we want? And that's the value function. So as we saw also earlier, our goal is to maximize what's called the expected return. So I get a reward at every time step. And if I sum these rewards up to the end of my trajectory, to the end of my decision-making process, then I have the total return, a total reward that I would get for that trajectory. And I want to choose my actions to maximize that. There's the discount rate gamma, which determines the present value of future rewards. It just says how much are future rewards important. So it gives you the possibility to have an infinitely long decision-making process and not go into infinity, so it helps mathematically, but it also gives you the opportunity to tune how much are future rewards important for right now, which is also important for real-world problems, where that is a relevant factor. And again, just kind of emphasize the point, if we knew what the expected return was for certain actions, given the current state that we're in, we would already know, we would have solved our problem. We would know what to do, we would just choose the action that maximizes that, and we would be done. I'm repeating it so often because it's very simple, but you can kind of get lost in it in all of these equations and definitions. And really our task is simple. We want to know what is the best action, and if I had the number behind that, I would know what to do. And this is the idea behind the policy and the value functions. Can we find a function which tells us how good it is for the agent to take a given action, given the state that we're in? Because if we can do that, if we can find this function, if we can figure it out, then we have solved our problem. And so let's look at that sentence a little bit more in detail. First, we need to know, I want a function that tells us how good it is. So I need to understand what I mean by how good. And I want to know how good it is to take a particular action now from the state I'm in, even though I have many future steps in the future. So how do I know what happens after this action I take? Because I don't necessarily know. So let's define that a little bit in more detail. How good is defined in terms of this expected reward, or expected return, sorry. So the sum of all the future rewards. And how do I know what happens after? Is that value functions are always defined in terms of policies. So the expected return is dependent on what actions I will take after the fact, after this one that I'm evaluating right now. And that's why a value function is dependent on the policy that I choose. Because I'm going to take the action I define right now, and after that fact, I'm going to take the action as given by this defined policy, and that will determine how I know what are the future actions. That gives me the possibility to define a future reward right now for a current action. Are there any questions? Mm-hmm.
Is there a reason why one would want the gamma factor, for example, to be 1? Because then, I kind of think of an issue in convergence or time convergence, or like sort of a problem maybe then not becoming physically computable anymore.
Yeah.
Or is there?
Well, I mean, if you have.
How easy is it to like get towards the direction of not being able to compute it anymore?
Well, I would say there's two answers to the question. There are cases where you have gamma is 1. Or, and Mars, did you want to answer that? Or? Sorry, yeah, to repeat the question. The question was, is there any case where it makes sense to have gamma equals 1, and how realistic is it to have gamma equals 1 given the fact that it could make things difficult to compute? And you could have a bounded system or a finite system where you only are allowed to have a certain number of steps, and then the problem becomes easy. In that case, you have a fixed amount. For infinite problems, then you need to have gamma less than 1. Because if you think about it, you could just have a trivial.
That's not true.
Okay.
You could still have gamma equal 1. You just need to look at the average reward you get, and you can still do it.
Yeah.
In my experience, actually, the gamma has little to do with the actual application.
That's for finite harassing problem, right?
Pardon?
That's for finite harassing problem. Depends on the MDP.
Even for the infinite horizon, you can do gamma equal 1 if you take the average reward.
It's a geometric series, right? So it doesn't really compare.
No, if you know that the rewards are declining.
Yeah, if you shape the reward, yes.
So it depends on the MDP.
It depends also on how you.
But in general, you can set in general, I can set it to 1 if it's an infinite horizon problem because there is no conversion.
Short answer is complicated.
So yeah, it's complicated. But, I mean, there are ways, yes, when gamma can be 1. I think everyone will agree if you have a geometric series that goes to infinity, with a sum, it will go also to infinity, and we can discuss that also. There's also other implications of that.
So if you have an episodic task and you know it will end.
Pardon me?
If you have an episodic task which you know will end, then it will not.
Yeah, but the comment was even in an infinite task, you can still have gamma equals 1 if you take the average reward over the infinite task, which is possible, I think. But yeah. So let's define what is the expected return when starting in S and following our policy pi. So I say I've fixed my policy, which says, given a state that I'm in, what actions will I take? And given that policy and given the state that I'm in S, the value function is defined as the expectation value of the expected return starting from that state S. And that's just this sum over all of the rewards taken from this point on, given the state that I'm in. I can also define an action value function, which is not just following the policy from this point, but I take a particular action. So I remove myself out of the policy for this action. I give you the action I want to take, and I follow the policy from this point. And that's my action value function, which is similar, also useful for different tasks. And it's then the expectation value of the expected return given the particular state and action that I'm in right now. And value functions, just as a kind of a brief comment, they can be estimated from experience, and that's really what we're going to be seeing in most cases. So how can I estimate this value function because I don't know it in advance and I can't calculate it because I don't have the, for example, the model I would need to calculate it directly. If separate averages are kept for each action taken in each state, so if I'm thinking about this action value function, then these averages will converge to their true values if I have enough samples. But if there, and this is something we'll see also in the future, if there are many states, it will not be practical to keep separate averages for each state individually. And that leads us into this whole field of function approximator methods, deep reinforcement learning, because you can use a function approximator to approximate your value function. So that's kind of where the ideas of deep reinforcement learning came out. Is there's a whole field of reinforcement learning which doesn't need a function approximator, but if I can use that, then I can use also the benefits of deep learning. But let's look at our very simple example now. So what would be the value function in our Mars rover example? In this case, I'm going to take an easy policy, which is to just always move right, because I can see on my screen that moving right seems like it's a good idea. And if I am to calculate this, and we'll learn how to do this in the next step, then the value functions that I get is what's written down below. So now I've only calculated the value functions for these middle states. And because of this stochasticity of sometimes you move to the right and you end up actually moving to the left, that's why you don't get always an expected return of 10 in every state. And the closer you are to the right, the higher it is, because then the probability that you end up going left all the way to the end is smaller and smaller. So this is the value function. This gives a little bit of a feeling of what does the value function actually mean? So how good is it to be in the state S2 in this, using this policy, versus how good is it to be in the state S6 given this policy that I have? And I think it's quite intuitive to think if I'm in S6, I have a pretty good chance of ending up with the reward 10. Whereas if I'm in the state S2, it's a higher chance that I end up on the left-hand side. Okay, so the next step is to talk about Bellman's equations. So now we have our value functions, but how am I going to get them? So I said we could estimate them. I said when we have them, we've solved the problem. But how do I get there? How do I estimate actually my value function? And a fundamental property of value function is that they satisfy recursive relationships. This means that the value function of one state can be written in terms of the value function of different states. So that's what recursivity means. And so let's think of a very simple case now. So this is a policy where there's only one action is taken from a given state, and it's deterministic. That makes everything very simple, and then it's very intuitive. If I'm in a state now, I take an action, I end up in a new state, and I get a reward along that way. That means the value function of the state I'm in now must be equal to the reward I get for that action plus the value of that state I end up in. So that's just, it has to be consistent. Which means that the value function of the state S is somehow related to the value function of the state S prime. When I take that action A, I went from S to S prime, I got the reward R, and so the relationship is with this factor R and our factor gamma. In the case where I go away from the simplest case, I end up with these expectation values, which just make it look more complicated, but it's the exact same principle. If I'm in a state now, and I take some action according to my policy, my value function can be written, so my value function is defined as the reward that I get plus the expected return from the next step I'm in. And if I break out this expectation value and I really just sum over all of the possibilities that I have based on my probability distributions from the policy itself and from the model itself, that's what the factor of the function pi and the function of p are doing there, and the sums. That's just breaking out the expectation value. You see that my value function of the state S is still related to the value function of the state S prime. And this defines what's called this recursive relationship between the value functions. And a similar recursive relationship holds for the action value function as well. So in the same way, the action value function taking the state S And at the state S, taking the action A is related to the action value function at the next step, at the next state, S prime, taking the next action I take. Now let's take one step further. We have these recursive relationships between our value and our action value functions. But what I said earlier is that in reinforcement learning, we're looking to find the policy that maximizes the reward over the entire episode. And that defines my optimal value functions. So now I say I'm not looking at any policy. I'm looking at the optimal policy, which is the best one. And that I'm going to note by this little star, which is, mathematically speaking, I'm just maximizing over all possible policies of this value function. I haven't said yet how we do that or how we know which one is the maximum, but that's the definition. We can do that for the action value function as well. So the optimal action value function is the one defined with respect to the optimal policy. And it can find a relationship between the optimal action value function and the optimal value function, also given here. And if I would have this optimal action value function, then I can choose an action by acting greedily. So again, I'm just defining what I'm looking for, and I'm looking for this optimal action value function, because then I know I just take the action that maximizes it, and I've solved my problem.
May I have a quick comment?
Yes.
Sept and Barto writes exactly like this, right?
Yeah.
And what puzzled me when I read this first was the following. When you maximize over the policies, it could be that in a different state, the maximization leads to a different policy. And now the question is there a policy where the value function V star is the value function of this policy? Is there an optimal policy? Because the maximizer could be different at different states. That's not clear, prima vista. One first needs an argument that there's actually a consistent policy where V star is the value function, and there is a policy, an optimal policy at all. And this is not discussed in Sept and Barto.
Yeah, that's true. Yeah, it's not. Yeah, you need to have a proof of optimality.
Yeah, right. That there is one, and then
Yeah.
then it's properly defined, and V star is the value function, and then everything works out again.
Yeah.
But this first puzzled me. Yeah. It's not so clear at first.
Yeah. Yeah.
That's actually a key insight here. Yeah.
Okay, so yeah, to repeat the question for the people online. To repeat the comment, the point is we need to, what we haven't done here is shown, that we haven't proven optimality. We haven't shown that we can prove that there is one unique optimal solution. If we were to have that, then this would be clear. Until we have that, this is based on that assumption. So going back to our relationships between our value functions, so we have our optimal value function still satisfies this recursive relationship. And if you look at this, this is just a system of equations. And so really, this is what's called Bellman's optimality equations, and this is just a system of n equations, if I have n total states in my system and n unknowns. And this is generally a system you can just solve. If I give you n equations and n unknowns, you can just solve it. They're nonlinear equations because of the maximum function. If they were linear equations, there's even more standard methods to solve them. And if I were to have, in order to be able to solve this, though, with all of the mathematical tools we have to solve nonlinear sets of equations, I need to know this model. If I have this complete model, then you see that this really does become a problem of solving a set of equations. And once I've solved it, like I said, you have your V star, and you can just maximize it and act greedily, and then you get your optimal behavior. But like I said, explicitly solving these equations, I mean, oh yes, go ahead.
And by model, you mean the P?
Exactly. By model, I mean this P function. And I use the word model for this, but model I think is used in a million different areas in a million different ways. But if I have this P function, because if I have this, then it really is just a set of equations. If I have all the numbers, I have all the I can actually just do this sum. So if I were to write this out, if I have 10 states, I could just write this out for all the iterations of all the 10 states, and then I would have a set of equations. Mm-hmm. If you have infinite.
Yeah, I mean, if I measure, for example, the position of my agent on a plane,
yeah.
and I do it exactly, then I have infinitely many positions.
Yeah.
Will I just narrow it down to a discrete space, or is there different? Because I assume
yeah.
it's not always possible.
Yeah, it's not always possible, and that maybe comes into this problems with. Sorry, no, the question was for the audience. What happens if you have an infinite number of states? So if you have a continuous state space, for example. And there's cases where this is not possible always to solve in exactly. So if I don't know my dynamics exactly, if I don't have the resources to compute it, the calculation, or if the Markov property doesn't hold. And in these cases, then what we try to do is approximate the solution in some way. So our goal is to find an approximate solution to this set of equations, which allows us to get around these requirements that we have here. And there's many different ways to do that. Each of these ways has advantages and disadvantages, and that's really the field of reinforcement learning, I would say, is understanding which requirements do I have, which information do I have, which information is important to me, and deciding based on that which method to use to approximate the solution to these equations. And so some of the things that we need to ask ourselves when trying to find an approximate solution is, for example, how many steps do I take before I try to make my next update? Is my update on policy or off policy? These are all things we'll look at concretely later on. Do I use a function approximator, or can I use a tabular solution, which is going now into your question of what happens when I can't make a tabular solution for my states and actions. And there's different categories of solutions, and the ones I'm going to talk about are these four here. I'm going to introduce them now, and then it's going to be the topic of the next lecture tomorrow. So the first category is dynamic programming. This is when we actually have a known model. So we actually have this P function for every state and action. We have the full transition and reward model, and then we actually can we can go through and iteratively calculate our value functions. So we don't calculate it exactly, but we calculate it numerically iteratively. And we actually are calculating exact expectations of the Bellman equations because we can. The second set of solutions is Monte Carlo solutions, and here our assumption is that, well, we don't have this model anymore. So what do? We need to make some samples and sample the behavior instead of relying on complete knowledge of the system. And so what we do is that we generate episodes by generating behavior, we generate trajectories, and based on those trajectories, we say we can estimate what was the model because we have a couple of examples which can approximate that. We use complete sample trajectories and returns, and something characteristic to Monte Carlo solutions is that you always wait until the complete end of the episode in order to make your updates. You always know what your exact reward was at the end, which will have some advantages and disadvantages. There's then temporal difference learning, which is a category of solutions which learns online. So it uses what's called bootstrapping in this case. It says, I'm not going to go to the end of my episode to get the true expected return, but I'm going to estimate it and use my estimate to make the next update. And this will converge then over time by always improving your estimate. The last solution category is policy gradients. So in Monte Carlo and TD learning, you're always working directly with the value functions and trying to make a direct approximation or estimate of the value functions. And in policy gradients, instead of going this workaround route of getting the value function and then deriving the policy from it, usually the greedy policy, you work with the policy directly. So you parameterize the policy, and then you optimize that parameterization in order to maximize your reward. And this uses then the policy gradient theorem, and we'll derive that later in the next lecture. So that's the summary. So today my goal was to kind of give the outline, give the fundamentals that we have. We know now, hopefully, what the problem is that we're trying to solve. We can write it out, we can define it, we can kind of quantify it even. And now in the next lecture tomorrow, we'll go into these different solution categories and see how they're used to actually find the optimal policy. So that will be the goal for tomorrow. And then Simon will take over again and go into more advanced topics other than what I've given here. And then even after that, Marius will talk about the more exciting stuff after that. So thanks. That's everything from my side. And we have time for questions if there's any questions. Yeah. Mm-hmm.
For all of the approximations, right, so if one wants to have a good approximation in the infinite case, doesn't one always assume there's some kind of symmetry or some related concept where, let's say, local information can give rise to global properties, let's say? Or
I don't think you always need to have some sort of symmetry. I mean, you're taking advantage of some sort of, unless someone else has something to say about it, but in some sense, if you use a function approximator, you're saying that, okay, I can use some sort of generalization. If I'm in the realm of this state, I can make statements about around, like what's happening around it. But otherwise, if it's just because it's infinite, I don't think you would.
Okay, so from the state on, you just are interested in the local property around, for the function around the state you're in.
What do you mean by that?
So given a certain state we are in, we want to approximate functions around the state.
I mean,
or do we want to have the global?
So I'm not sure what you mean by the global answer, but say I'm taking a tabular method for the value function, then it doesn't really matter, because then I'm really solving for each state. I'm trying to understand its properties regardless of what's happening around it. It doesn't matter. If I'm using a function approximator, then I do make some assumptions about the behavior of the function and that it's continuous, and I can make that it's differentiable, things like that. But in principle, if you have a tabular case, one state doesn't really care about the others, unless you want to say something?
Just say that for the continuous case, when you have an infinite set of states, you have prior knowledge on where to find the data, for example. You can definitely build your own feature extractors and convert the state to an observable that you can understand due to these states too. So if you have prior knowledge, you can always be smart about how you provide information to the agent. So let's say you have a heat map, and it's just a Gaussian. You might not need to give the entire 2D heat map. You just give a profile of the center, for example, and it might still be enough for the control problem. So I don't know if it's on the same question that you asked.
Mm-hmm.
Questions? I have a mic.
Okay, if not, then I think the next point on the agenda, we have coffee break and we have the photo at 5:15. Are they picking us up from the coffee area for the photo?
Yes, maybe in front of the lecture hall.
Okay, so everyone who wants to be part of the, in front of the lecture hall, if you don't want to be in part of the photo, don't come. But please come, because it's good for us.
Der verwaltet alle Audio- und Videoressourcen sozusagen.
Ja, genau.
Sehr cool.
Test. Test, Test. Test. Test.
Ja, du kannst verschiedene Modi einschalten. Welche in der Version? Aber das funktioniert mit beiden. Ja? Man sieht's.
Aber geht das Mikro auch? Ihr hört es. Ah, passt. Okay. Cool.
Ganz kurz noch.
Schön.
Gibt es irgendwo, das ist ja voll cool, also drunter liegt ein Check. Also das
Nein.
nicht, ja.
Der geht direkt auf die Also-Devices. Genau. Und bitte Pulse Audio kompatibel ist an, also für Clients ist es ununterscheidend. Ist es transparenter Wechsel von Pulse Audio auf Pipewire. Mhm. Now I think.
Okay, great.
Can you say something just to test?
Yeah. Can you all hear this? Is that coming through?
So.
Kann man die Audience zeigen kurz?
Let's see. I think that should be working. If there's any issue, I can try to switch to a different microphone. Okay,
so perfect. We can hear you, and you should be also able to. Also, the audience can hear us. Awesome.
Great, and my screen is visible to everybody.
I hope there is no delay in the acoustics. Can everyone please?
For a second.
So could you state something, Sergey, to check the sound?
Yeah, can everybody hear this? Is that working?
Not really sure. There is some sort of acoustic issue. Just give me a second. Maybe I can turn a bit louder.
Okay. Yeah, if it's on my end, let me know. I can also try to switch to a different microphone.
Does this work? Is this maximum? So. So, everyone, thank you for being here. Sergey, thank you very much for joining us. Today I have the honor to introduce Sergey Levine to you. He's a associate professor at UC Berkeley and also leads the Rail Lab at Bayer. He's a very remarkable figure in the field of reinforcement learning, had several publications amongst guided policy research and soft actor critique, for instance. He earned his PhD at Stanford and basically worked also on even topics that I've been in the past very interested and still looking into data-driven RL, for instance, offline reinforcement learning, amongst others. Without any further ado, thank you very much for being here in our session, Sergey, and the stage is yours.
Great, thank you. So today I'm going to talk about reinforcement learning with prior data. And what I want to tell you about in today's lecture is the foundations of offline and offline to online RL algorithms, as well as some applications. When I was preparing this talk, I thought about talking about applications in robotics, but I figured that maybe the robotics stuff is like a little better known, so I wanted to talk about applications in a few other domains, but that will hopefully give you a nice cross-section of where these methods can be used. Let's start with a little bit of motivation. So these days, there's a lot of excitement about data-driven generative AI. So these are models that will generate images that look like the kinds of images that people might draw, generate text, respond to questions, power AI assistants, and that sort of thing. Fundamentally, modern generative AI is a very kind of fancy version of density estimation, modeling the distribution of X or the conditional distribution of Y given X. And in some ways, this is like a massively scaled up version of what you learn about in statistics class when you learn about how to estimate a distribution. And of course, if you have a system that is estimating a probability distribution, of course, the most important question to ask is which distribution is it? And for generative AI systems, deep down, the distribution that they're really modeling is the distribution of content that people create and put on the internet, the kind of pictures that people take, or the kind of sentences that people write and post on the web. So it actually makes a lot of sense when viewed in this light that generative AI systems should be very good at emulating human behavior, because if they are literally trained to reproduce the distribution of content that people put on the internet, it makes sense that they would generate pictures that look like pictures that people would draw and text that looks like the kind of text that people would write. Reinforcement learning is also a very exciting AI technology, but its strength is actually very different. So one of the most well-known kind of pivotal moments in reinforcement learning was move 37 in the AlphaGo Lisa et al. Championship match, where the AlphaGo system made a move that surprised even human observers, where they didn't think that this was a move that human experts would have thought to make. So it was an emergent behavior. And it's interesting to contrast that with the kind of impressive things that we see with generative AI. The generative AI systems are impressive because they produce content that looks like the content that people would make. The reinforcement learning system is impressive because it comes up with an emergent outcome that is different from what any person would do. So that's a very different kind of strength. Now, in the same way that these types of AI methods have very different strengths, they also have different weaknesses. With data-driven or generative AI, it learns about the real world from data, typically data produced by humans, but it doesn't really try to do better than the data. There's been, of course, a lot of excitement lately with things like thinking models for LLMs that do try to go beyond the data, but fundamentally the basics of generative AI are trying to match the data distribution. Reinforcement learning is all about optimizing a goal with emergent behavior, but typically reinforcement learning methods are notoriously bad at making use of real world data. So the AlphaGo system was trained using billions and billions of simulated games of Go. And of course, it's easy to simulate games of Go. It's comparatively harder to simulate billions of trials in more realistic tasks. So data-driven AI is all about using data. Reinforcement learning is all about optimization. And the trouble is that data without optimization doesn't provide us with a way to solve new problems in new ways. It simply provides us with a tool for emulating what we saw in the data. But optimization without data is hard to apply to the real world outside of simulators. So that's also really limiting. So ideally, what we could develop in the future is a reinforcement learning recipe that uses lots of data to understand how the world works via some kind of data-driven offline RL pre-training phase, and then uses what it learned in that phase to have a fast and safe RL fine-tuning loop where it builds on that prior knowledge to discover emergent solutions to new problems without necessarily emulating exactly what it saw in the data set. So the data can come from lots of sources, and if you build up the right body of prior knowledge, then perhaps you can acquire new behaviors very quickly that go beyond what the human solution looked like. So if there's sort of one overarching question to this lecture, the overarching question is, what can we accomplish if we combine data and optimization? So can we basically get the best of both these worlds? And what I'll talk about is first, the foundations of data-driven RL algorithms. These are what are called offline RL algorithms. And then I'll have two sections to discuss applications. I'll discuss applications to generative models for generating images, and then I'll discuss some applications to language models. Of course, there are many other areas where these could be applied, but I wanted to pick those two application areas because they kind of nicely illustrate a cross-section of domains where maybe we don't ordinarily think of RL as being like a very central tool, but we can actually apply it if we have the right methods. Okay, so what is it that we need to figure out to develop data-driven reinforcement learning techniques? So classical RL is framed as an online feedback loop. You have an agent that interacts with the world, gets some data, improves its policy, gets some more data, and repeats. In data-driven RL, you start with a data set. You use that data set to figure out the best policy or value function, basically the best starting point, and then you might have an online reinforcement learning loop. So in classical RL, we typically emphasize the fact that it's an online and lifelong learning process. We are most concerned about the performance that we can attain when we train from scratch, and learning is largely driven by trial and error. So the kind of problems that we often spend a lot of time on in classical RL are, for example, exploration. If you've never seen that MDP before, how do you achieve full coverage so that you will discover sparse rewards? So central problems are exploration, sample efficiency, and optimization performance. How high can the final reward be? How strong can the Go playing agent become? In data-driven RL, oftentimes the kind of things we're concerned with, the research bottlenecks, are a little different. We always start from data, which means that the challenge of exploration is, well, not entirely eliminated, is greatly reduced. And it's largely representation learning driven. So the central problems that we often deal with are things like distributional shift. What happens when your policy deviates from the typical behavior you saw in the data, can you still make sure that you can evaluate policies that are different from the behavior you saw before? Scalability and stability. Can you get these methods to scale up to the setting where the data sets are extremely large and the models are extremely complex? And representation learning with big models. What goes wrong when you start using, for example, transformers with billions of parameters as opposed to small convolutional networks? So the central problems in data-driven RL tend to much more closely reflect the kind of challenges that we see in large-scale machine learning in other areas, as opposed to these very optimization-centric issues we see in classical RL that are much more focused on learning from scratch. So to break this down a little bit, the kinds of things that we need to sort out if we are to develop fully effective data-driven RL recipes is number one, offline RL methods, meaning that first phase, take a data set and learn something useful from it. Online fine-tuning from offline initializations, and making all of this work with big scalable models. And truth in advertising, we have a pretty good understanding of number one, a somewhat of an understanding of number two, and actually a relatively poor understanding of number three. And I'll talk about each of these things, although of course the things where we have a poor understanding of, I can only provide you, what we know, which is maybe not that much. Okay, so let's start with offline RL. What do we expect offline RL methods to do? Like, what is the problem that they're solving? So one very simple problem is if you have like a starting location and an ending location, and you have a bunch of data that shows how the task can be done, how you can go from the start to the end, you can try to imitate that data. That is not what offline RL methods do, although that is a very basic version of learning from offline data. What offline RL methods do is actually a bit more sophisticated. A good mental model for this is that you have your starting location and ending location, but instead of data that shows exactly how to do the task, you have a lot of data that shows things you could do in that environment. And what you would like to do is take this diverse data and figure out what you can learn from it that will allow you to compose bits of what you've seen to find a better behavior, one that gets a higher reward than anything you've seen in the data. And it makes sense that you can do this because sequential processes in time are naturally compositional. So if you've seen a way to get from A to B and you've seen a way to get from B to C, you ought to figure out that it is possible to go from A to C. So you're basically leveraging the fact that in an MDP, you have this compositionality in time, and that compositionality in time can be used to do better than the typical behavior in the data set. So this A to C kind of example is like a very crude instance of stitching together different behaviors you've seen in the data set, but that's just the clearest example. You could also imagine a much more nuanced example where maybe you have many behaviors that are all a little bit suboptimal in different places, and if you can take the most optimal part of each behavior in each place, then overall you'll do much better. Imagine that you're learning to drive a car, and you have data from many human drivers. Different human drivers are better or worse at different things. So if you can compose behaviors so that you are as good as the best human driver in each situation, then on average, you will be better than any human because you're as good as the best one in each case. Okay, so to dive into a little bit of the technical foundations, let me give you a quick primer to value-based off-policy RL methods, describe what challenges arise when we try to apply them to the offline setting, and then describe briefly a few different paradigms for modern offline RL. So in reinforcement learning, we have an agent that interacts with the world, and the agent chooses actions A, and the world responds with states S and rewards R. The agent is supposed to select actions according to a policy that it learns, and the policy is learned to maximize cumulative expected reward, meaning the total reward that we'll get over the course of an episode. It could be infinite horizon or discounted. Here I have the finite horizon undiscounted case, but that's all kind of the standard stuff. A really important object for reinforcement learning is what's called the Q function. So the Q function depends on a particular policy, and the Q function tells you if you start in a state ST and then take an action AT and then follow the policy pi, what is the total reward that you will get? And if you can determine the Q function for a policy pi, then you can recover a new policy that is as good or better, typically better, by simply being greedy with respect to the Q function. So always taking the action with probability 1 that is the argmax of Q. And that's the essence of policy iteration. You can also short circuit all of this and simply train the Q function directly by regressing onto the reward plus the maximum of the Q value at the next step. And if you can find a Q function Q star that satisfies the Bellman optimality equation shown here, where the left-hand side is equal to the right-hand side, then the greedy policy for that will be the optimal policy in the absence of approximation error. So that's basically the essence of Q learning. So Q learning just says, let's take the left-hand side of this equation, the right-hand side, subtract them, and minimize the difference. Now, importantly for this discussion, if you can minimize the difference between the left-hand side and right-hand side of the Bellman equation at all states and actions, then you will get Q star. And in practice, you can do so at samples, assuming that you generalize, and those samples could come from any policy. So that's why Q learning is an off-policy method. It doesn't assume that the state action tuples that you're training on come from any particular policy. Okay, so that's the main idea in Q learning. Now, this might suggest on the servers that we could simply take this concept and directly out of the box apply it in an offline setting where the agent does not get to interact with the world anymore, but simply starts with a static data set, runs Q learning on that static data set, and gets back the optimal Q function. Naively, this does not work. And one of the big advances in offline RL was the emergence of a full understanding of this problem in the early 2020s. So what is the problem with naive Q learning? Let me rewrite the Q learning equation in a different equivalent form that will elucidate the problem a little bit more. So we could just as well write the target value as the expected value of QS prime A prime under some distribution pi nu, where pi nu is simply a policy that takes the argmax of probability 1. So I didn't actually change anything about the equation. I just wrote it in a different way that makes it apparent that in order for that Bellman backup to work, you need to be able to estimate the expected value of Q under another distribution called pi nu, which typically would be this greedy policy. And if you can do this accurately, then it will work. And if you can't do it accurately, then it won't work. But now, Q is a neural network. And if you want to learn, if you want to ask whether a neural network will accurately predict expected values under some distribution, then the question you want to ask is, what distribution is it trained under? Because when the training distribution matches the test distribution, then everything works. If they don't match, then generally things do not work. So what is the objective? Well, the objective is to minimize the difference between the left-hand side and the right-hand side of the Bellman equation under the distribution of states and actions seen in the data. In offline RL, we typically call this the behavior policy. The behavior policy is the policy that generated the data set. So you want to minimize the error under the behavior policy, but then you want to test it under pi nu. So that means that this works if pi nu is the same as pi beta. But how often is that the case? The whole point is that pi nu is a better policy. In fact, even worse, pi nu is selected explicitly to maximize the Q values, which means that it is a kind of adversarial example. It's actually finding actions for which the Q function will output the largest value. And we know that with neural networks, we can often trick them. We can give them inputs that will force them to output the value we want if we're willing to optimize over their inputs. And pi nu does exactly this. It optimizes over the inputs into Q. So we would expect, based on what we understand about adversarial examples, that this Q learning procedure applied in an offline setting would lead to exploitation, meaning that it would lead to policies that pick actions that are not actually very good, but that fool your Q function to thinking they are good because the Q function is trained under the wrong distribution. And that's exactly what we see in practice. So the curves in the bottom right show an offline RL value-based method. On the left side is the true reward. You can see that for different data sizes, the true reward hovers around minus 250. On the right side is the estimated Q values. The y-axis here is actually on a log scale. So it's 10 to the power of whatever it says on the y-axis. So for that blue curve, the reward is around minus 250. The Q value thinks it's going to get 10 to the 20th power. So massive overestimation, massive exploitation with those adversarial examples. So what that means is that in order to get value-based RL methods to work in the offline setting, we have to somehow address this problem of distributional shift. Now, there are many different methods for addressing this problem, but there are kind of a few themes, and most methods in the literature will revolve around these themes. So the first theme is use value-based methods. So Q learning or Q function actor critic, essentially the core of modern offline RL methods is going to revolve around estimating value functions, which are typically Q functions. That's not including model-based methods. Of course, model-based methods can also be very effective, and that's a separate discussion. And then The second thing is somehow fix the distributional shift problem. And that could be done in a few different ways. And I'll outline 3 broad themes, and many methods fall into one of these themes. One way is to use pessimism. Pessimism means for actions that you have not seen before, unless you have evidence to the contrary, assume they are bad. So that would mean that for any of those out of distribution actions that might exploit your Q function, basically robustify your Q function to think that they're actually not very good. It's very similar to adversarial training, which is a known mitigation for adversarial examples. The second class of solutions is to use policy constraints, meaning use some kind of actor critic method and constrain your actor to not be too far away from the behavior policy. This, by the way, is the kind of approach that is most commonly used in language models. So, for example, when a PPO has a constraint to a reference policy, it is essentially an instance of this kind of policy constraint. And then the third class of methods, which is maybe a little exotic, but I'll actually talk about these a little bit more later, is to figure out a different way to set up Bellman backups that avoids out-of-distribution actions entirely in your updates. And I'll talk about a particularly widely used instance of this called IQL later in this lecture. So let me give you now a few examples of sort of high-level outlines of offline RL methods that fix this problem as kind of illustrative examples of these themes. And I'll talk about 2 of them. I'll talk about conservative Q learning, and I'll talk about implicit Q learning. And these will not be in-depth kind of tutorials. I just want to give you a kind of a one-slide summary so that you know the overall recipe, and then you can take a look at the paper if you want all of the details. So the first one I'll talk about is conservative Q learning. And conservative Q learning is sort of a classic instance of a pessimistic method that tries to fix this overexploitation problem by essentially correcting out-of-distribution actions. So the principle at a high level behind CQL is that if you have some kind of ground truth signal, like this green curve, and you fit it with this blue curve, your fit might be pretty good on average. Like you can see in most places, the blue curve is pretty close to the green curve. But if we take the maximum of the blue curve over here, we'll essentially pick the point with the highest positive error. So that's bad. That's what leads to these adversarial examples. So what we could do is we could pick out those points and we can explicitly lower their value. So in CQL, there's the regular objective, which is the one shown at the bottom. And that's basically just like exactly the left-hand side minus the right-hand side in that Q learning equation. And then there is a CQL regularizer shown at the top, which looks a little bit like a GAN. So if we look at what this is doing, the first term is minimizing the Q values under pi, and pi is chosen to maximize the Q values. So basically, pi seeks out those high value actions, and then that first term in the regularizer pushes them down. But now the trouble is if you have only that term, you're going to bias your entire Q function downward, and you will actually underestimate. So the second term in the CQL regularizer, which has a negative sign in front of it, it takes the states and actions in the data set and pushes them up. So now let's think about what that regularizer will do. Let's imagine that pi is equal to pi beta, meaning that the high values are all for the in-distribution actions. The first term will push them down, and the second term will push them up, so they will actually cancel out. So in the case where all of your high-value actions are in distribution, the CQL regularizer does basically nothing. But in the case where you have some out-of-distribution actions that have a high value, the first term will push them down, some other action that's in distribution will get pushed up, and the entire policy will shift more towards the behavior policy. In terms of the formulation, this does look a lot like a GAN. It's also mathematically very similar to adversarial training, so it kind of makes sense that this would mitigate the problem because the problem also looks a lot like the problem of adversarial examples. Now, there are a lot of details in terms of how to implement CQL effectively, and I would leave those to the paper. These kinds of methods, because they have this adversarial nature, can be a little trickier to implement, but they can work very well if set up correctly. And there's also some nice theoretical guarantees, and in fact, I should say that a lot of the theoretical analysis of offline RL methods and a lot of the provably convergent methods are based on some kind of pessimistic regularization. All right, the second class of methods I want to tell you about is implicit Q learning. And this is, again, something that has been followed up quite a bit in more recent literature, but I want to kind of describe the basic recipe. Implicit Q learning is based on a different principle. In implicit Q learning, we don't try to fix the Q function to do something special about out-of-distribution actions, but we instead try to set up a different version of the Bellman backup where we never have to query for actions that are not in the data set. So here's the idea. let's say that you have two trajectories, and those trajectories pass through some states that are pretty similar, shown as these green circles. So now you might infer that for the behavior policy, at least, the value function at those two green circles is probably very similar, because even though for one trajectory went off to the left, for the other one it went off to the right, they pass through very similar states, so probably those states have about the same value, and then it's all the stuff that happened downstream that explains why these trajectories ended up being different. So if this trajectory had a total reward of -10, and this trajectory had a total reward of +10, then maybe the average value you'd get at those green circles is actually somewhere around 0, because about half the time you go left and half the time you go right. Now, that's basically the essence of function approximation. So here the Q value is -10, here the Q value is +10, but we know that probably the difference in that Q value is not due to the difference in state, it's probably more due to the difference in action, because the states are very similar, but the actions ended up being very different. So if we implement the following kind of learning algorithm, we first minimize the squared error between the Q function and R plus the next value, and then for the value function, we minimize the squared difference between the value and the Q value for those states and actions. If we do this, then we'll recover a value function that basically predicts a value around 0 at this state. And this is basically SARSA. It's just SARSA broken up into two function approximators. So it's basically predicting the average value for the policy in the data set. Now, the interesting thing about this method that I described is that just from looking at these equations, you can see that we only ever use the states and actions in the data set. So nowhere in here do we have a maximization operator. Nowhere here do we ever have any distributional shift. Of course, we're estimating the value function of the behavior policy, so we're also not improving over the behavior policy. So this by itself is not good enough, but it doesn't suffer from the distributional shift problem. So this won't give you a much better policy because there's no policy improvement in these equations. It'll just give you the value of the policy that collected the data. But now let's think about that second line, V equals min over V of the squared difference between V of S and QSA. Remember the intuition that because at that green circle, we see that there were two similar states, but two different actions leading to two very different values, we can kind of imagine that underneath this, there's a kind of histogram representing the frequency with which different values occur at a particular state. And if we have a function approximator that generalizes, we might kind of understand that about half the time at that state, you get a -10, and half the time you get a +10. So you could think of the value function of that state as determining some statistic of this distribution of values. And when we regress onto Q with squared error, the statistic that we get is the mean. So we're basically averaging together the different Q values we've seen in that state, and that's why they average out to 0. But now, what if we don't take the mean? What if we actually take an upper quantile? What if we ask, at this state, what are the best values you've seen? Now, of course, the upper quantile is going to be closer to 10. So you'd basically say, like, because in states like this state, I've seen -10s and +10s, I'm pretty sure that I can achieve a +10 if I were to enter this state, as long as I execute the right policy. So what we could do is we can actually change that V equals equation. Instead of regressing onto the mean of values at that state, we can regress to an upper quantile, or what's called an upper expectile, which is another statistic that basically captures the upper range of numbers. And it turns out that we can do this simply by using a different loss function. Instead of using squared error, we can use what's called an expectile loss. So if you think of squared error as a parabola, the expectile loss is basically kind of like an asymmetric parabola, where the positive errors are penalized differently from the negative errors. So it kind of makes sense that if you basically penalize errors in one direction more than the other, then you would skew your regressor towards the larger values and away from the smaller values. And it turns out that you can prove that this will actually get you what's called an expectile, which is kind of like a quantile only for squared error instead of absolute value. So that's basically the idea behind IQL. It's almost like SARSA, but you modify the loss function for regressing the value function towards these larger values. And that will get you a kind of an optimistic SARSA, which basically tries to learn what is the upper distribution of values, the upper statistic, for similar states. And that can actually provably get you close to the optimal value function if done right. And crucially, there's no distributional shift because the learning algorithm never even has to ask for any action that was not in the data set. Okay, so that's offline RL. Now let's talk a little bit about online fine-tuning. So it turns out that when you're doing offline RL followed by online RL fine-tuning, it's often not that simple. And this is now, we're getting into the territory where there are some solutions, but I would say there isn't like a perfect solution yet. To illustrate the challenge to you, let's imagine the CQL algorithm. Although every offline RL algorithm has some version of this problem, with CQL it's a little bit easier to explain. So this is a CQL algorithm again. And if we train with offline RL and then do some online RL fine-tuning, you get a pretty interesting problem. So here at around 50,000 steps, at the point where that red stuff starts, we switch from offline training to online training. And you can see that there's this very sudden dip in performance. So in offline training, you got to some good performance, then you start collecting online data, and suddenly performance drops. So online training starts here at 50,000 steps. And that period highlighted in red was kind of wasted time. Like that's time when your method started getting online data, lost performance, and then spent a lot of time recovering that performance before it could get back to making progress. And this is very typical for offline pre-training followed by online fine-tuning. If we look at the average Q value in the data set, we can see that over the course of CQL training, the average value drops and drops and drops, which is kind of what you'd expect because it's a pessimistic method. And then as soon as you start collecting online data, it actually spikes again. Why? Well, because you were very pessimistic about those out of distribution actions, and now you started actually collecting data for those actions, and you see that they're a lot better than you thought they were. So suddenly there's this really strong learning signal, but that learning signal isn't really real. Like it's not actually teaching you a better policy. It's just sort of correcting for whatever regularization you put in during the offline phase. And this is most obvious for pessimistic algorithms, but the same thing happens with other methods. So with IQL, you'll start suddenly getting actions that you never trained on. With other methods, you'll start getting some other pathology. It all kind of revolves around the same theme, which is that all those new actions coming in that were from a different distribution than the one that you pre-trained on require a big adjustment period for your method to sort of catch up before it can start making progress again. And during that adjustment period, you often lose a lot of performance, which you then have to waste time recovering. Okay, so it's different offline RL methods have different versions of this problem, but there's always something like this, and it's actually very hard to fix this completely. In fact, this problem is so hard to fix completely that an embarrassingly strong baseline for offline to online RL doesn't actually use offline pre-training at all. So this is called the RLPD algorithm, Reinforcement Learning with Prior Data, which is a way to use offline data for online RL that completely dispenses with pre-training and simply preloads the replay buffer during the online phase with offline data, but then learns entirely online. So the value function and policy are initialized entirely from scratch, but every time you sample a batch from the replay buffer, you mix it half and half with a batch from offline data. You would think this would be pretty bad because you're starting from scratch, you're not pre-training, but it's actually a surprisingly good algorithm. So initialize two buffers, initialize the value function active from scratch, and then you run online RL, and then for every batch, you just sample half of it from the offline data and half of it from the online data. This works very well. It outperforms a lot of dedicated offline to online methods that actually use pre-training, and it's actually like an embarrassingly difficult baseline to beat. And the fact that it's such a difficult baseline to beat actually is not an indication, I think, of how good RLPD is. It's actually an indication of how difficult the problem of pre-training with offline RL and then fine-tuning with offline RL really is. So this is, I think, deeply unsatisfying, and it's really hard to beat with any proper offline to online method. So I'll tell you about a few research papers. Like this is now getting into the territory of like fairly recent research work, because I would say doing this right is kind of an open problem. And I'll tell you about some of the ideas that have been pretty successful lately to hopefully inspire you if you want to do research in the same area. So one method that we developed recently is called Warm Start RL, which tries to deal with this problem. So the idea in Warm Start RL is actually not to keep the offline data at all. It's actually to pre-train with offline data and then throw it out and then run online RL training with a warm-up phase that is designed to mitigate this dip, this problem where performance degrades once you start online training. So we pre-train on offline data with offline RL, and then we use a warm-up phase where the policy doesn't change to burn in during online learning. So in this warm-up phase, the value function is adapting to the new data that's coming in, and the policy isn't allowed to change so that we don't lose performance. And then we run regular online RL after that based on a variant of soft active credit. So Warm Start RL, labeled in blue WSRL, actually works very well. And perhaps interestingly, it actually typically works as well or better as compared to offline to online methods that actually retain all the offline data and perform offline pre-training. So here, orange, red, and purple are 3 different instances of methods that do offline RL pre-training and then online RL while retaining all the offline data. And green is RLPD, which doesn't do offline pre-training. Blue is not always the best method, but it's the best method the most consistently, meaning that while there's a different method that sometimes matches or slightly exceeds its performance, it's often not the same method. So that's pretty good. That means that, like, if you want a reliable recipe that kind of tends to work pretty well, this one is a good choice. And it does experience a dip, but the dip is usually pretty small. Okay, so these are all the methods that keep the prior data in the buffer. And here's a video of a real robot learning with this method, and this is pre-trained on the FNB data set and then fine-tuned for peg insertion, and it like learns pretty quickly in about 7 minutes of real-world training. So 7 minutes is pretty fast. This is from Pixels. So 7 minutes to learn a robotic skill is, you know, quite nice. So that's really showing the power of offline pre-training. Another method that we've developed recently, which takes a different approach, is called diffusion steering. So diffusion steering is leveraging diffusion models to acquire a more structured action space. So the idea is this, that conventionally we would take our data set and try to run some fast online RL method, and the problem, of course, is these out-of-distribution actions from the offline data set. So this is kind of the problem that I discussed before, that your policy might choose actions that are outside of the distribution that it saw in training and get an erroneously high Q value. But now imagine that we take our offline data set and we train a diffusion model with imitation learning. Now, for this diffusion model trained with imitation learning, for every noise sample that goes into the diffusion model, it'll map to some in-distribution action, because that's literally what the diffusion model is trained to do. So that means that if we treat the noise that goes into the diffusion model as an action space, every single sample from the prior of that noise is an in-distribution action, which means that if we do RL in the diffusion model noise space, there are no more out-of-distribution actions, and we can safely run very sample-efficient online RL algorithms like soft actor critic without worrying about OOD actions at all. So it's kind of a transformation of the action space that essentially, by construction, eliminates out-of-distribution actions. So the key idea is run a very efficient online RL method in the latent space of a diffusion model like DDIM or flow matching. It's important to use a diffusion model that has a deterministic mapping from noise to action, so not DDPM, but DDIM or flow matching. And that's basically the entire idea. So it's actually a very simple concept. And typically we would do this with a very large and powerful diffusion model to represent the mapping from noise to action, and then a smaller actor-critic pair for RL that just operates on the noise space. This method is actually so efficient that we can run reinforcement learning with it on a real robot. Obviously, the diffusion model is pre-trained on lots of data of a variety of tasks from this robot, and we can learn skills in about 50 trials, which is very, very fast. That is basically minutes, with rewards that are directly provided by a person. So the person running this experiment is literally sitting there pushing a button to give the robot +1 or -1 rewards to teach it in real time how to do the task. So I can fast forward this a little bit, and you can see here that as the robot goes, like it gets a few more successes, and then over time, after about 30 trials, it starts getting successes pretty consistently, and after 50 trials, it will reach close to the optimal performance. This is a very fast method for online RL. It's also a very fast offline RL method because you're essentially eliminating all out-of-distribution actions. So in practice, it can get close to the performance of state-of-the-art offline RL methods in offline mode as well. Okay, so the last kind of conceptual topic I wanted to cover is, what about making all of this work with really big models? And this is where now we go from things that are at the cutting edge of research to things that we don't really fully understand at all, but that are kind of open problems. So we've done quite a bit of work on all sorts of algorithms for large-scale offline RL, for example, training on lots of different Atari games, things like that. I won't go into detail about this because I want to get into the theory. But what makes this really hard is, like, it seems kind of annoyingly hard to make offline RL, value-based offline RL methods work with really large models. And it seems to require larger models with more capacity than we might expect. So if you train them with imitation learning, maybe you can get good performance with like a medium model. When you do this with RL, it turns out you need a model that's even bigger. And that's kind of mysterious. So something about temporal difference learning, value-based learning, seems hard in supervised learning. and it's not clear what that is. So we've done a lot of experiments to try to figure this out. So these are some experiments that Aviral Kumar did. He took the game of Breakout and trained a value function just with the behavior policy. So there's no maximization. And looked at average Q values. If you take the behavior policy and you back up actions sampled from the behavior policy, so S and A come from the data set, and then A prime is resampled from the behavior policy, you get this kind of exploding value problem over time where the average Q values blow up. They become very large if you train for long enough. Interestingly enough, if you use exactly the next action in the data set, meaning you don't resample it, so A prime here comes from the data set, it's the same distribution, it's just a different sample, then the values don't blow up, and that's the red line. So this is kind of interesting. We're not even doing maximization. We're just learning the behavior policy value function. We have two ways of doing it. One resamples the next action. The other one uses the action in the data set. The one that resamples blows up. The one that doesn't resample does not blow up. And that's very weird because statistically these should be the same. Once we start looking at the features inside the network, meaning we take the last layer in the neural net and we look at the dot product between the features of the current state in action and the features of the next state in action, we see that their dot product actually blows up. So it's not just the last layer weight, it's actually the features becoming unstable. So phi here is the features in the last layer of the neural network, which you then dot product with the last linear layer, and that's what gives you the values. So something about the representations inside these models explodes when they're trained on next actions that are not in the data set. Okay, so what does this mean? The surprising finding that we had, and this is coming from some theoretical analysis, is that TD learning actually hurts internal representations. And that's kind of what these graphs are basically showing. The features inside the network are blowing up. To understand why TD learning might hurt internal representations, we first have to ask, why do deep nets actually learn good representations in the first place? Because deep nets are over-parameterized, so it's a little mysterious that they would work at all. And the most widely accepted model in the deep learning community is that there's a kind of implicit regularization effect that happens when you train deep networks. And implicit regularization basically says that among all the different solutions that you can get to a deep learning problem, the one that you actually do get is the one that minimizes some regularizer R while driving the loss to zero. And the regularizer has different forms depending on the kind of analysis you do, but roughly speaking, it's something like minimizing the norm of the representations or minimizing the norm of the parameters, basically trying to find a low norm solution, which is to say a simple solution where your network isn't like extremely jaggy, but is relatively smooth. So that's good, like finding a simple solution subject to the constraint that you minimize your loss seems like a good thing. It turns out that when we apply the same kind of analysis to temporal difference learning instead of stochastic gradient descent, we come to a different conclusion. That temporal difference learning also has this minimization effect, but it also has this this bottom term, which I know the equation is a little complicated, but I'll roughly describe it, which basically maximizes the norm of the features across different time steps. Exactly the same thing that we observed empirically. Meaning that instead of getting a low norm solution, you get a solution that minimizes the norm at a given step, but also maximizes the dot product between the features at the current step and the next step, which is to say that the features might blow up. And of course, these terms are balanced and the constants matter. And for that reason, sometimes it'll blow up and sometimes it'll not blow up. Now, long story short, if we kind of forget about the complexity of the math, what this suggests to us is that the very thing that makes representation learning work so well for supervised deep learning might also make it work not so well for temporal difference learning when we have target values that come from the same network, which is to say that TD has a representation learning problem. There are kind of various solutions you could put forward to this, but I think fundamentally this problem is not solved, and it's not entirely clear as of yet how to conclusively address this problem. Okay, so I'll skip this slide. There's a lot of work on addressing this kind of thing, but nobody has found a complete solution yet. Okay, so summary and takeaways. Offline RL is an essential component of data-driven RL, and we have to handle the distributional shift problem between the offline data distribution and the new policy. Online RL fine-tuning from offline initialization presents new challenges, and we have to be able to fine-tune via online RL without losing the benefits of the offline initialization. And this is something that there are methods for doing it, but they're not quite as solid. And then doing all this with large models presents yet more challenges, and there are some fairly substantial algorithmic and theoretical challenges to be addressed here. So if you're looking for open problems, this is a reasonable place to look. Okay, a question for the organizers. I believe I have 45 minutes for this, right? Okay, cool. So in that case, I should probably stop here and go to questions. The applications are fun, of course, but I think the conceptual material is a little more important to get through. So I'll probably end the talk there and give you guys a couple of minutes for questions.
So, questions from the audience?
Thomas. Actually, I have a question, yes. Yeah, maybe you come down that we have not a feedback problem. Unfortunately, we had to change the computer, so we could not use this yet.
But maybe first of all, thank you very much, Sergey, for also.
Yeah.
Speaking here and also here.
Okay, so I have two mics now. Seems how to work out. I'm just curious about, as you told us about this warm start approach, right? It seems a bit,
yes.
It's related to a neuroplasticity problem, right? It looks a bit like, you know, washing basically the learned task out by starting the new one. How would you state on that? This is basically going towards this direction that you cannot really learn tasks sequentially with a neural network?
That's a good question. So there are actually several problems that happen with offline to online RL. So there's always the kind of the classic problem that has to do with continual learning, meaning that if you train for one task and then you start training another task, then you're going to get some issues. Like one issue that you'll get is if you train on the first task for too long, then your model might lose plasticity and learning the second task might be harder. And that's the issue that you're referring to. There's a second problem, which is more RL specific, which is that if you are collecting additional data as you go, meaning that it's an online RL process, then in the process of learning the new task, changes to your policy will affect the data that you collect. And it's actually that problem that we're trying to solve here, meaning that as your policy changes when you collect new data, if your model degrades, it might go back up later, but if it degrades, there's a kind of a positive feedback loop, meaning that if your value function gets worse, now your policy gets worse, now your policy collects worse data, that worse data is even more different than what you saw, so now your value function gets even worse, and now your policy gets even worse, and as a result, we get this, this dip that I showed here. That's a different problem in many ways than plasticity. So the warm start RL method is not trying to do anything about loss of plasticity. That's still very much a challenge. It's just trying to address this feedback between data collection and the model, resulting in everything getting worse and causing that dip. But the plasticity issue is not solved by this. And there's been lots of really interesting work. Clara Lyle, for example, has done lots of work about plasticity and RL. There are some mitigation strategies, but it is not being solved by this method.
Thank you very much. Any other questions? Otherwise, in the meantime, I'll ask a question. How is it about also learning maybe from, usually as we are also learning from observations of other agents, if you want so, in the world. That's usually a transposition problem, specifically also important for robotics, right? Do you have any literature thoughts on this, and then maybe especially with offline data from third-person perspectives or other basic perspectives?
Yeah, that's a really tricky problem. So there are a couple of things I will say here. So when you're learning from kind of passive data like this, there are two challenges you face. One challenge is the domain shift problem, meaning that whatever you're observing is basically has a different action space or a different embodiment than you do. The second problem is the lack of actions, meaning that conventionally in RL, we think of data as sequences of states and actions, but in the passive data case that you're describing, typically you get only states or only observations and not actions. For the domain adaptation problem, that one is tricky. Like I think it's very hard to have like a universal domain adaptation solution, but basically the way that domain adaptation is handled is you either translate the source domain to the target domain, meaning to use some kind of explicit mapping, like translate it with a diffusion model to like change the images. Or you use many domains and then generalize over domains. And these are the kind of things that have been explored very well in computer vision. And in my opinion, like it's something that is kind of well left to the kind of computer vision world, because it's not actually an RL specific problem, although it is an important problem. For the second issue, the fact that you get only states and not states and actions, that is actually an RL problem. And it's actually possible to develop RL methods that can leverage data without actions. And the key here is the fact that the value function, V, is a function of only states. The Q function is a function of states and actions. So you can use data with states and without actions to learn value functions, and then much more efficiently, with a limited amount of data with actions, recover the Q function from those. And there have been quite a few works on doing this. My student, Dibbo Ghosh, who recently finished his PhD, he has a paper called Intention Conditioned Value Functions, ICVF, which proposes a very general framework for doing this. But there are many others as well. So basically the key there is use data with only states to learn value functions.
And as a follow-up, maybe quickly, do you also see goal-conditioned RL, for instance, as a way forward? Because that is sort of a, as you stated, a bit computer vision perspective, because you could basically rotate and translate the problem.
Yeah, I think that's a great point. And in general, like I will say that when it comes to large data sets and kind of modern large-scale machine learning settings, I think goal-conditioned RL is actually like a very appealing paradigm. Not because we necessarily want agents that reach goals, but because goal-conditioned RL can be done very easily and very cheaply on all data that is available. So it's almost like saying, like, if you get lots of data and you don't know what you're supposed to do, just learn all the possible things you can do using that data, and that should give you a really good starting point for other things to figure out later. And I think that's a very promising direction. Actually, one of the applications that I had to skip actually talks about goal-conditioned RL in the language model setting. You can actually train language models to reach language goals, and that's a pretty powerful way to learn diverse capabilities. So I think that's a really interesting thing to study.
Very nice. Please. You have to still come. It's on the laptop.
All right, yes, so I think if I interpret this right, it would basically argue for, if you have a lot of data, a huge data set, it would, in a, would say, actor-critic sense, would make sense to learn the critic upfront, right, with the data you have, because you just have to learn the value function then, which gives you a more elaborated approach to learn the policy, right? Is this the message, the more or less takeaway message for this part?
Yes, yeah, I think so. I mean, generally, if we want RL algorithms that are efficient and model-free, then basically the difficult part is learning the value function. So the way this breaks down is that if you want to do RL with data, you really have two options. You can do model-based RL or model-free RL. In this lecture, I only talk about model-free RL. If you want to do model-free RL, then you have to learn the value function, and the value function is basically the difficult part. Once you learn the value function, extracting the policy is comparatively easier. If you do model-based RL, then you need to learn a model. And then you use that model to recover a policy. And that actually maybe illustrates what's really going on, because in both cases, you're learning a model. It's either the model is a model of the value function or it's a model of the dynamics. And you've got to get one of those two, and that's the only way to do RL with data. And the language model crowd often actually learns a model, which is the language model. And for robotics, for other kinds of applications, typically we would learn the value function. But they actually kind of serve the same purpose.
Awesome, thank you. Anyone else? Please, if you can.
Maybe you can just translate.
Yeah.
Exactly.
It's very simple. I will tell it to you and then you can...
Yeah.
So when we want to fine-tune, let's say, supervised model, we usually do not fine-tune the parameters of all the model, but maybe the last layer or the bias. I think there might be a smaller dip if only
So your question, so the question is basically if the whole model was fine-tuned of the language model, if you mean now, with your reference, from the offline to the online case that you presented, or was the full model fine-tuned or trained, or just the last layers, for instance, in the neural network?
Oh, I see. So for most of the applications that I presented, there isn't anything special being done in that respect. Like for the robotics cases, the same exact thing is trained in the offline phases and the online phase. There are lots of optimizations you could do. Like if you're really working with giant models, you can do things like fine tune only the head of the model, and there are some complex reasons to do one or the other. Obviously, if you want the most efficient thing, and if you're lucky enough to have a good starting point, then you could try to do stuff like that. For the diffusion project that I presented there, it's important to emphasize that the RL algorithm was only training a separate small network, a small MLP that operates on the noise space of the diffusion policy. But for everything else, it's kind of generic with respect to that.
Thank you. Maybe as a follow-up from my side, specifically, are there parallels, do you think, between actually having let's say, a language model as a base model and then fine-tuning it with RL and the offline to online cases? Because in my opinion, this is there are a lot of parallels there.
Sorry, I don't think I fully understood the question. So the parallel between what and what?
So if you say, because we talked about world models also quickly beforehand, and the idea is a language model can be seen as having a huge world model of the words basically, and now you usually have RLHF or several other algorithms on top of them. Fine-tuning, is this are there some parallels between offline RL with online fine-tuning and versus language models to online?
Yeah. So I think the parallel is basically that the value function serves a similar function as a predictive model, because what the value function is really doing is learning to make counterfactual predictions, basically a prediction that if you were to take a different action than the one that you actually took in the data set, what would happen? Like that's why all these distributional shift challenges are a problem, because fundamentally you're asking this thing to make counterfactual predictions. And if you have a world model, it's kind of trying to solve the same problem. Now, a value function is different from a world model because a value function essentially averages together all those possible futures. So you can think of it as basically predicting an average over futures instead of explicitly producing the entire future. Whereas a world model tries to actually predict the entire future step by step. But it's kind of a different path to the same endpoint. The reason that world models might be easier to train than value functions is that world models are in principle independent of the policy, whereas value functions are policy specific. So this is actually like, at the heart of this is a deep open problem in reinforcement learning, which is model-based RL versus model-free RL. What are the strengths and weaknesses of both? Under very simplifying assumptions, like linearity, they can actually be made exactly equivalent. But under practical conditions, it's actually still an open problem as to when one is preferable over the other in a statistical sense. And this is kind of surprising because it's been studied for decades, but people actually truly still don't know, is there a reason to prefer model-based over model-free in the general nonlinear function approximation case?
Yes.
There's a question up there.
Sir, please.
Just a curiosity, if it exists some sort of approach to interpret these reinforcement learning models, so to justify the decision-making process.
So the question is if there is a way to interpret the decision-making process of the reinforcement learning algorithms in a way, visualize, or I assume several kinds of.
Oh, I see. That's an interesting question. Well, all of the methods that I described today are inscrutable, generic, and used with big black box networks. So there we can't figure out anything, basically. What I will say that might be kind of interesting to you is there is interesting work that people have done kind of maybe in the background a little bit over the years that looks at how models trained with language can be used to provide interpretability. There's like lots of newer works for this, but a particularly clear elucidation of these principles is actually in a paper by Jacob Andreas. He's now a professor at MIT, called Learning with Latent Language. It's a pretty cute paper where what he does, he trains a policy that is an instruction following policy. So it takes in a language string. And then when he goes to solve new problems, he doesn't fine-tune the policy, he actually fine-tunes the language string. So it's like prompt optimization before prompt optimization was a thing, and uses this as a tool for interpretability. And there are many newer works that kind of build on that general philosophy. I'm not an expert on interpretability, so I don't know if that's necessarily like a good approach, but it's something kind of intriguing that people have studied.
Thank you. Some other questions? This is your chance. If not, then yeah, please.
Okay. Hello, Sergey. One question, we discussed model-based versus model-free, and you mentioned the gap if you try to fine-tune, right? So I'm wondering if you also try to somehow leverage meta-reinforcement learning techniques to mitigate this gap when you switch from offline to the online setting, to prepare the agent in a way that it knows more or less what it might expect in terms of uncertainty.
Yeah, I see what you're saying. So essentially, you could have a kind of an offline phase where meta learning is used to almost like simulate prospective online fine-tuning scenarios. I think it's a really interesting idea. I have not seen anybody do that in the model-free setting. I'm not sure I've actually even seen anybody do it in the model-based setting. It's just that for model-based, it's like a little easier to think about because there you can essentially use the model to simulate all sorts of possibilities. Yeah, it's a really intriguing thing. I haven't seen that. The closest that I've seen in the literature is using hand-designed physics simulators to simulate adaptation and then use that to prepare policies that can adapt in the real world. But that typically relies very heavily on a hand-designed simulator that actually provides, uses domain knowledge to provide those alternative situations. It's a good idea, though.
Yeah, thanks. Cool.
Good. Any other questions? If not, then we thank again Sergey. Thank you very much for your time. It was really a pleasure having you.
Thank you all for listening, and thank you for the great questions.
Is it important for everyone? It's for dinner. So thank you for the online audience. We will be from tomorrow again back.